Hello students, welcome to the class. So today is our day 16 of this JEE 40 days crash course, and the chapter we will do today is the electrochemistry part. Now if I talk about electrochemistry, then it is divided into two parts. The first one is related to conduction. Okay, so in that part we learn about electrolysis and the law of electrolysis, and also about conductivity, conductance and similar terms. The second part is related to your Nernst equation and your batteries. Okay, so that is the second part. Now this is the total division of a chapter, and today we will cover the first part, which is our conductance, conduction and all related terminologies, and then after the two laws of your Faraday. Okay, so Faraday first law and Faraday second law. So quickly join the class. We will begin our class in a minute. This is the disclaimer. Now before moving on to the chapter, let us see that what is the percentage weight of the marks from this chapter in your JEE exams. So there is a 4.16%, and at least one question is included in your every paper of every shift in both the sessions in the previous year. Okay, of course this chapter is important because questions are asked from it directly, and sometimes you will see that there is an application question. Okay, so this chapter is famous for its application question rather than direct formula related questions. Now moving on to the important topics. If I talk about 2024, then questions were asked from electrolysis, the part which we are going to cover today. So in that we were asked about the Faraday's law. Now if I talk about 2023, then again you can see questions from Faraday's law and cell potential and cell constant. So this was a year in which mixed questions were asked from all topics in different shifts of different sessions. Okay, you can see questions from Faraday's law also, as well as from the Nernst equations also, which is the second part of our chapter we will be covering tomorrow. Then if we move on to 2022 and 2021, then again we will see questions from Nernst equation, cell constant and electrode potential, whereas in 2021 we will see questions from molar conductance. So you can clearly depict that this whole chapter is important because questions are asked from every part. In comparison to other chapters, where such as your some basic concepts of chemistry or your redox reaction, where questions are asked from specific parts. Here we can see questions from every part of the chapter. Okay, so this is a big chapter, and we will try to cover the first part of it. Then if I see in the year 2020, 2019, 2018 and 2017, then again we can see questions from electrolysis, the first, and the Faraday's law. So most of the questions are from the Faraday's law. Then the conductance, conductivity and other related terms, and third type of question is asked from your Nernst equation and its equilibrium constant calculation. Got it? So moving on to the topics that we will cover today. So first we will see the metallic and electrolytic conduction. The chapter is named as electrochemistry, and the most important thing is that here we are interested in electricity, which is based upon electrolytes. So we have studied about electrolytes in our ionic equilibrium chapter. There we saw that electrolytes are those substances which produce ions on putting it in the solution. Now these ions are responsible for the conductance of electricity. So these type of electricity is under your electrochemistry. The second type which we see in our daily life. Okay, so first type is also there in our daily life, but it is not seen directly. Suppose you take the example of battery. It involves the application of electrochemistry. You take the example of inverter. There also the battery which you are seeing is based upon the electrolytic cell. Got it? Whereas the metallic case, you see it in the wires. Okay, so the conducting wires that you are seeing, there the electricity is based upon this metallic conduction. Now first we will understand this electrolytic conduction, and then we will try to measure it, or I would say then we will try to quantify it. Means in every aspect of your life you want that electricity must be supplied in a appropriate amount. Now, how do we control that amount? By looking upon certain parameters. So for metallic conduction, resistance is very much valid and good for this quantitative measurement. But in case of electrolytic condition, we use conductance rather than resistance. Okay, so we'll study about that conductance, and then we'll study about specific conductance and conductivity, which is represented by kappa. Moving on to the next part, which is molar conductivity. So this part is mostly important for your lab experiments where we are interested in molar properties. Then we have equivalent conductivity. So we'll try to difference between these two, molar conductivity and equivalent conductivity. Now once you know that what are the parameters to judge electricity amount, we will move on to the first application, which is electrolysis. Okay, so electrolysis must have been taught to you in your previous classes also. In 9th 10th we have seen that your impure metal strip is made pure by using this electrolysis. Okay, so you must have seen that we take a impure copper rod, we take a pure copper rod, then we supply electricity by an external voltage or a battery. There the impure copper is converted, or you can say it is deposited on the pure copper rod. Okay, so that thing is known as electrolysis. So we'll try to study that in detail. Next, we will move on to the Faraday's law of electrolysis. Okay, so two laws are there, first law and second law, and it is very easy to get that law. I will try to explain every aspect of that. And the important part I would say is your formula part. In this whole chapter you will see various formulas, but they are related to each other. Lastly, a very important law which is known as Kohlrausch law. So this thing is something which is used to calculate molar conductivity. So first we will see what is molar conductivity, and then this Kohlrausch law is used to calculate that molar conductivity. So let us begin with the first topic, which is metallic and electrolytic conduction. So substances that conduct electricity are known as conductors, and those do not conduct electricity are known as insulator. So this is the thing, you know it, it's very simple. Now further, conductors are of two types. First is of metallic conduction, the second is electrolytic conduction. In metallic conduction, electrons move as in metals. Okay, so free electrons are present in metals and they are present in the conduction band, and they are the one responsible for conducting electricity there. But in case of electrolytic conduction, the species which are responsible for moving the current is your ion. Okay, not electron but your ion. So ion move in the solution and they conduct electricity. Got it? So remember, you can just move to a very quick position that the movement of ion is the main key factor in determining the current in your electrolytic conduction. More easily your ions are propagated throughout the solution, easier will be for that ion to conduct electricity. Got it? Now, as I said earlier, what are metallic conductor? You can just write the definition if you want. They conduct current by transfer of free electrons, and this process is known as metallic conduction. Whereas the electrolytic conductors, they conduct electricity by mobility of ions, or means the ease with which an ion can move into a solution. So this is known as electrolytic conduction. Now, next, so our target is to study about this electrolytic solution. The first part, which is your metallic or electrolytic conductor, you know it very well. It is well covered in your physics part. Okay, so here we are interested in this electrolytic solution. Now, as I said earlier, the best parameter which is used in the case of your electrolytic solution is your conductance. Okay, rather than using resistance, we use conductance most of the time. Now, what is conductance? It is simply the power of an electrolyte to conduct electricity. Now, similar to your metallic conductor, electrolytic solutions also obeys our Ohm's law, which is V is equals to I into R, where V is your potential, I is your current, and R is your resistance. Okay, so similar to that, Ohm's law is also followed in the case of electrolytic solutions. So each and every law will be applicable here also. Now, How do we define this conductance? We have seen the statemental condition for it, but what is the mathematical formulation of this line? So it is very simple. It is simply the reciprocal of resistance. Okay. So here also resistance is there, but since, as I said, conductance is much more applicable to your electrolytic solution, so we will use conductance most often, and it is defined as reciprocal of your resistance. So G is the way to represent this conductance, and it is equals to 1 by R. Now, what is the unit of conductance? So it is very obvious. If ohm is the unit of resistance, then you are taking reciprocal of ohm. That means ohm inverse. Now we also call it as mho or Siemens. So these are the three units that are used in your conductance unit. Got it? Is it clear to you? Anyone who has a doubt till this part? So you must know the basic difference and the basic motive behind your electrolytic condition, where the ions are responsible for conducting electricity, and ions have a tendency to move through the electrolytic solution, which is measured in terms of your conductance, and conductance is equals to 1 by R, which is resistance. So its unit is ohm inverse or Siemens, which is capital S, or mho. So anyone who has a doubt can post it here in the comment section. Or if you don't have a doubt, you can just send the thumbs up so that I can get an idea how many of you are attending our class. Is it clear to all of you? Anyone who has a doubt in this? Okay, I assume that it is clear to all of you. Now, moving on to relation between resistivity and specific conductance. So resistance of any conductor is varied with the length and cross section area A. Now what is length and what is cross section area? Whenever you take electrolytic cell or any electrolytic conductor, what is there? Electrodes are present there, right? So you take two electrodes and with the help of potential you conduct electricity. Now the distance between the two electrodes is your length. Got it? And the area which is present there in between is known as the cross section area. So your solution must be present in a container, and the cross section area of that container is known as the area. Okay, so as simple as that. And the distance between your electrode is known as the length, which is represented by L. Now your resistance is directly proportional to length and inversely proportional to area. Now we can just formulate it mathematically and write it as R is directly proportional to L by A. Then further we can move this proportionality constant and place a rho here. So this rho is something which is known as resistivity. You must have studied about this and seen this formula also in the physics part. R is equals to rho L by A. Now this resistivity is also known as specific resistance. Okay, now why are we telling it as specific resistance? Whenever we try to keep or constant the parameters to a certain value, we name it as specific resistance. For example, if you take the example of heat capacity, right? So we simply call it heat capacity if the amount of substance is not defined. But if we are taking it for 1 gram of a substance, we call it as specific heat capacity. Got it? So from the same logic, if your length and area are kept to one unit, then in that case we call it as specific resistance. So here what you are taking? You are taking a specific value of resistance where the length of your system is 1 centimeter and area is 1 centimeter square. Got it? So we are taking a specific condition where your resistance is equals to rho. In that specific condition, your length is 1 centimeter and area is 1 centimeter square. Now, since the unit is taken as centimeter, we are taking our whole system in CGS unit. If your system is having a different parameter or a different dimension, you can also take it as meter. But remember, the value should be in 1. Okay, you can define it in different units if you want. in SI units, in CGS unit, but the value should be 1. So here we are trying to define it in CGS unit. Got it? Now, next, what we do, we take the reciprocal of this rho. Now, how do you remember this? In the previous slide, we said that when we are taking the reciprocal of R, we are getting conductance, which is represented by G. Then here what we are doing, here we are taking the reciprocal of your resistivity or specific resistance, and we are naming it as specific conductance, because here we are taking specific value but for conductance and not for resistance. Got it? So we name it as specific conductance, and it is represented by kappa. So this is not K, it is kappa, and we can just write this formula, rewrite this formula for 1 by R, and it will be L by A multiplied by R, 1 by R, okay? And in place of 1 by R, we can write conductance. So we can finally write here specific conductance kappa is equals to 1 by rho is equals to L into A into conductance. Got it? Now, what is this L by A? As I said earlier, they are the dimensions. So L is the distance between your electrode and A is the cross section area of the container which you are considering for conducting electricity. Now these two are something which are fixed, okay? So if you have built an electrolytic cell, then you can't change its dimension, okay? You can only change the solution, you can change the concentration, but it is difficult to change your dimension of your electrolytic cell. That means this is something which is always constant for a given electrolytic cell, both your length and area. So we are taking a ratio of both this constant, which will be again a constant, and it is named as cell constant, okay? So length by area, or length is to A, is known as cell constant, and this thing is very, very important. You will see questions from it on a regular basis. This cell constant is represented by G star, okay? So conductance is represented by G, and your cell constant is represented by G star. Next, what will be the unit of your specific conductance? It's very simple. We remember that conductance is simply 1 by rho, so it will be ohm inverse. We can write it here. And L by A means centimeter by centimeter square. So length is having a unit of centimeter in CGS term, and your area is having a unit of centimeter square in CGS term. So centimeter by centimeter square, that means centimeter inverse. In place of per ohm, you can also write it here Siemens. Okay, so it can be also Siemens per centimeter. Is it clear to all of you? So these formulas are very, very important. So we started from resistance. We said that if we take the reciprocal of resistance, we will get conductance. Then there is a relation between resistance and resistivity, which is R is equals to rho by L, rho into L by A. Further, if we take the reciprocal of rho, we will get what? We will get specific conductance, which is kappa. Got it? So two things are important. First is the relation, and second is the representation. Like conductance is represented by G, specific conductance is represented by kappa, cell constant is represented by G star. Now it is not formal that it will be used with the same symbol, but still it will help you to remember formula. So try to keep this notation same while remembering them or while using them. Okay. Now moving on to the next part, which is molar conductivity. From the term also you must have gotten an idea what is this molar conductivity. I will give you the definition also. So first of all, this molar conductivity is denoted by lambda m, and this molar conductivity can be also written as molar conductance. Got it? So this is something which is weird and it is used in most of the cases. So molar conductivity and molar conductance both are same. Remember, this is very, very important. Okay, although conductance and conductivity are different, but molar conductance and molar conductivity are same. Now how do we define it? It is the conducting power of all the ions which are present in 1 mole of an electrolyte. Okay, that means you take 6.022 into 10 to the power 23 particles of that electrolyte, and the conducting power that is owned by that 1 mole is known as molar conductivity. The most important part is your formula, which is lambda m is equals to kappa into 1000 by molarity. So why are we telling it as kappa by molarity? Because we want to define it for per mole. And we know that molarity is number of moles per unit volume. So if we keep molarity in the denominator, then we will get it for per mole. Now next thing is important, which is multiplication by 1000. So this is varied, okay? It depends upon the unit you are taking your calculations in, okay? Since molarity is always represented in terms of mole per liter, so we want it to convert it into centimeter, and for that reason we are multiplying it into 1000. If your molarity is already presented in mole per centimeter cube, which is not seen in most of the cases, but if it is present, then in that case you are not uh, prohibited to multiply it with 100. Only if and if only it is represented in terms of mole per liter, or it is represented using capital M, in that case we will have to multiply it with 1000, so that every length unit should be in centimeter, because 1 liter is equals to 1 decimeter cube, and to convert this decimeter cube into centimeter cube, you have to multiply, or you would say you have to divide this molarity by 1000. Okay, I hope this part is clear to you. It's very, very important. Now, what are these terminologies? You know it very well. Lambda m is your molar conductivity or molar conductance. Kappa is your what? So it was 1 by rho, okay, which is conductivity. This is conductivity, right? Then what will be the unit of this molar conductivity? So just try to find it out. You can derive it by yourself. Suppose we start from kappa. So kappa has a unit of ohm inverse centimeter inverse. Further, molarity. What is the unit of molarity? If I write it in terms of CGS unit, it will be mole per centimeter cube. Okay, since we are dividing this molarity by 1000, your molarity will have a unit of CGS term. Okay, so it will be mole per centimeter cube. Now, centimeter inverse multiplied by centimeter cube will give you centimeter square. You can just try it out in your notebook. It's very easy to do so. But units are important. There was a direct question from the unit determination itself, and it's a very easy part to score. So I would force you to please try to derive this units by yourself. Okay. So two units are used here: per ohm centimeter square per mole, or Simon centimeter square per mole. So we have simply replaced this per ohm with the Simon. Okay. So any doubt till this point? Is it clear to all of you? Can you just tell me if you have a doubt here, or if you are going good with this lecture, just send a thumbs up so that I can get an idea you are probably getting my points. Anyone who has a doubt till this point? So we have covered conductance, then we moved on to conductivity, resistivity, right? And now we have tried to understand this molar conductivity. Is it clear to all of you? Anyone who has a doubt in this part? This formula is very, very important. Questions are asked from this formula multiple times. Okay, so let us move forward. So next is your Debye-Huckel-Onsager equation. Now this equation is very, very important to calculate your lambda naught m. Now what is lambda naught m? Question must arise in your mind. So basically, whenever you take an electrolyte, got it? And that electrolyte is a strong one, means it is a strong acid or a strong base or a salt. So these are the three conditions for an electrolyte to be a strong electrolyte. Got it? So if you take a strong electrolyte, their conductivity, okay, means their ease to propagate ions in the solution becomes easier and easier as you lower the concentration. Okay, so if you keep on lowering the concentration, your lambda m will increase, means your molar conductivity will increase. Now there is a certain value after which your molar conductivity cannot be risen further, but that point is not achieved practically. So to know that value, we use a mathematical formula. So let me explain it again. Molar conductivity of a strong electrolyte always increases on decreasing the concentration. Got it? And there is a maximum theoretical value which is important to get for your calculations and all, but that theoretical value cannot be uh, get from the practical terms. So we use a mathematical formula to do so, and that mathematical formula is your Debye-Huckel-Onsager equation. So you should remember two things here. The first thing you should remember is that it is only applicable to strong electrolytes. Got it? Second thing you should remember is that your conductance or molar conductivity of your Debye-Huckel of your strong electrolyte increases with decreasing concentration. Got it? Now that equation is lambda m is equals to lambda naught m minus A root C. You can clearly see that molar conductivity at any given concentration is inversely proportional to concentration, because this is a negative term. Okay? So if you keep on increasing concentration, the lambda m will increase. This A is a positive term. You will study about this in the higher classes. But remember, it is a positive term and concentration can never be negative. So if you keep on increasing concentration, the highest value of lambda m is lambda naught m. So your highest value is being decreased by some amount if you keep on increasing concentration. So this is simply your molar concentration. So we can write the terms here. Lambda m is the molar conductivity. Then lambda naught m is the limiting molar conductivity. Since it is the highest value for your molar conductivity, we name it as limiting molar conductivity. From this value, we can't move further. Okay. Then next we have A, which is known as Debye-Huckel constant. And lastly, we have C, which is concentration. So if you keep on increasing the concentration, this negative term will increase more and more, and hence your lambda m will decrease. So the electricity provided by your ions decrease by a strong electrolyte if you keep on increasing the concentration. I hope this is clear to you. Got it? Now, next, can we just plot it here? So the plot of this Debye-Huckel-Onsager equation is asked in your exams. It is also very, very important. So let me give you some important points before that. We can have a similar type of change in the weak electrolytes also. The same thing is observed there also, but the amount of lowering by decreasing the concentration is not that much significant. Is in the case of strong electrolytes. But in the case of weak electrolytes, if you keep your concentration low, if you do your concentration lower and lower, you will see a significant increase in the molar conductivity in case of weak electrolytes. Again, I am repeating my point. It's very, very important. You will see it in the graph also, that if you lower the concentration, then the effect on the increase of this molar conductivity is very high in case of weak electrolyte as compared to strong electrolyte. Okay. So there is a rapid increase in the value of equivalent conductance if you keep on diluting the solution in case of weak electrolyte. Similar to that of your strong electrolyte, we have a limiting molar conductivity value for this weak electrolyte as well. So after a certain value, you will not see a increase in the molar conductivity, and you name that value as lambda naught m. So you can see the graph here. See, if you see this it for strong electrolyte, then it is certainly increasing, okay, by some amount. But if you see the graph of this weak electrolyte, suppose for acetic acid, your increase is very certain, okay, very sudden. You can see a steep slope here, meaning if you decrease the concentration even by a small amount, your molar conductivity will shoot up. Okay, you will see a shoot up site here. Got it? So it's very, very important, and these two graphs are very, very important for calculating the lambda naught m. Is it clear to all of you? It's a very important point that you should remember. So what did I say? First of all, I talked about this Debye-Huckel-Onsager equation, and Debye-Huckel-Onsager equation is only applicable to strong electrolyte. It says that lambda m is equals to lambda naught m minus A root C. So if you keep on decreasing the concentration, or you can say if you keep on diluting the solution, you will see a change in your molar conductivity, and your molar conductivity will increase. But the change is not significant in case of strong electrolyte. It is much more significant in case of weak electrolyte. And that is very clear from this graph as well. I hope this part is clear to you. Now, if this is clear, now we can move on to electrolysis. So everyone, is it clear to all of you? Can we move on to electrolysis, or do you have a doubt in the previous part? You can ask it right now. Any part that is not clear to you regarding your conductivity and all? Okay. So I am assuming that you all got my point. If you still have a doubt, you can just post it in the comment section. Meanwhile, I will move on to this electrolysis. Shall I? Anyone who has a doubt in this? Or is it clear to all of you? And if you don't have a doubt, then please send a thumbs up so that I can get an idea that you are getting all of my points in this given lecture. So we are moving on to the next phase of this electrochemistry, which is electrolysis. Anyone who has a doubt till this point? Okay. So next, what is electrolysis? As I said earlier, this is basically used to clean a sample of your metal that you got. So this is, I would say, an industrial process which is used to clear the sample of a given metal that is obtained during mining and all. Now, how it works? So basically, in this process, we apply electricity and we do chemical process. So there are two things. First is electrolytic cell and second is this electrolysis. So in electrolytic cell, what we do is we apply your chemical process to do a electrical work. Here what we are doing? We are doing opposite of that. So this is basically a conversion of energy, and here we are converting your electrical energy to chemical energy. Basically we are trying to perform a non-spontaneous chemical reaction by applying an external factor, and that external factor is your electricity. Now what happens here, if we take an aqueous solution of a given metal and if we supply electricity onto it, then cations move from the cathode to the anions towards the anode. Okay, so two things are there. Cations move towards the cathode and anions move towards the anode. Now, the reduction and oxidation changes occurs at respective electrodes during electrolysis. Remember always that oxidation will take place at anode and reduction will take place of cathode. And this is true for both electrolysis and electrolytic cell. Okay, this is very important point. Questions are asked from here in the theoretical sense, that you have to decide that which one is showing oxidation and which one is showing reduction. So oxidation will act upon the anode and reduction will act upon the cathode. Now we will move on to selective discharge of ions. So if your given solution has more than one ion, then your selective discharge means the conversion of your ion into neutral species is decided by certain factors. I will talk about them. So I will give you a list. Then it will be more clear to you. So if I talk about cation, then how it is decided? So for cation, those species which are less stable, for example, if you take sodium, potassium and all, so they are less stable. In that case, the discharge of such ions are very much easy. Now, what are we doing in this process, in this electrolysis? So let me just give you a imagination. So we have a impure rod. Okay, suppose we have an impure rod of copper, which is containing a lots of impurities. Got it? In the right hand side, we have a pure rod. Okay. Now what we do, we dip both of them into a solution of copper sulfate. So the metal which you are trying to purify, you will take the same molten solution of that in a given container. Yes, I am from IIT Kanpur. Okay, so what you do, you dip two electrodes, one is of pure form, one is of impure form. So I am keeping your pure form on the right hand side and impure form on the left hand side, and we are dipping both of them in the solution. Now if you apply electricity, then what will happen? The electricity will break down your impure form. So suppose your copper is present here in the impure form, so it will be broken down, then it will be dissolved in the liquid solution. After that, it will move on to the pure copper rod, and slowly your impure part is converted into pure part and it starts depositing on your copper rod. Got it? Now here what is happening? Your copper 2 plus, which is present in the solution, it is going to a neutral form, right? So first it is discharged into the solution, it becomes an ion, and then it goes through the solution and it is deposited upon to the right hand side. So this conversion of copper 2 plus to copper, so that thing is supported by the reactivity of metal. Okay, so if your reactivity of metal is less, it will try its best to go into the solid form or neutral form. So you can say that the species which are highly stable, they will try to be neutral, or you can say they will try to discharge. So this Au3 plus and Ag3 plus means silver and your copper, silver and your gold, both are very much eager to go into the neutral form because they are highly stable as compared to sodium and potassium, which are highly reactive metal. So they have a less tendency to go into the neutral form. Now that same can be said about the anions. The anions which are more stable, they will be remaining into the solution, or they will not try to discharge, whereas the anions which are not that much stable, they will quickly try to get into the neutral form. So it is totally dependent upon the electronegativity. You know it very well that chlorine is more electronegative than bromine. Therefore, it will have a larger tendency to remain into the ionic form or the anionic form. Whereas iodine, which is less electronegative, it will quickly try to go into the stable form. Why? Because it is less electronegative. So I've already started this lecture series, and my lectures are present for the some basic concepts of chemistry as well. For each and every chapter, you can get our detailed lecture as well as our crash course lectures. Okay, you can just go there and visit our website. You will get the recorded lectures from here, and then still if you have a doubt, you can just come to our doubt session, which goes from 10 to 6, and there we will try to solve your problem. Okay. Is it clear to you? And I would suggest you to be with us during the lecture sessions also. Got it? So these are independent lectures. Although you don't have an idea about previous part, I am trying to put these lectures as independent. Okay, each and every lecture. Okay, so don't worry. Now, next, since we have talked about electrolysis, we have talked about how the process is going on. Now we will try to quantify this electrolysis, and that is done by the first law of electrolysis. Okay, Faraday's first law of electrolysis. It says that the amount of deposition of your metal on the pure metal electrode is totally dependent upon the electricity, and I would say it is directly proportional to electricity. More electricity you provide, more will be the conversion of your aqueous form into the solid form. Means if your given metal is present in ionic form, it will have a greater chance to move into the neutral form if you supply more and more electricity. Now, how can we write it mathematically? So it's very simple. We write it as W is equals to ZIT. Now where it is coming from? I said that amount of metal which will be deposited onto your metal electrode is directly proportional to the amount of electricity you are supplying. So we can write here W is directly proportional to Q. Then we can just remove this proportionality sign and introduce a proportionality constant known as Z. Okay, I will tell you what this Z is. This is known as electrochemical equivalence. We will talk about that and how to calculate it. It's very easy to do. Okay, so some students find it difficult. I will try to put it in simple words. Now, what is this Q? So Q is equals to IT. You know it very well. That current is equals to charge by time. Therefore, Q will be equals to IT. Now let me define these terms for you. So W is what? W is the mass of the metal which is deposited, or if it is a gas, then it is the amount of gas which is liberated. So there are chances that you are dealing with gas as well. Suppose you are taking chloride gas or chloride ion. Okay, so when it will be converted into your neutral form, it will be liberated as chlorine gas. Now next Q is the charge, which here we will take it as coulomb. Then we have I, which is current in amperes. Then we have time in seconds, which is represented by T. Lastly, we have Z. Now you must know how to calculate the Z. All of these terms, which is W, I and T, it is something you can easily know from the question itself. But Z is something you have to determine. How do you calculate it? What is this electrochemical equivalent? Now you have a chemical equivalence in case of your chemical equation or your chemical process. Similarly, in the case of electrochemistry, we have electrochemical equivalent. How do you calculate it? Simple formula, Z is equals to equivalent weight by 96500, which is your charge due to 1 mole of electron. Now, what is equivalent weight? You know it very well. It is equals to atomic weight by valency. Suppose you are dealing with copper, then you will take the atomic weight of copper and divide it by its valency. Means the charge which is present on your ion during the movement. Is it clear to you? So you must know how to calculate the Z. This is very, very important. Okay. It is given as equivalent weight by 96500, and equivalent weight formula is already known to you. It is atomic weight by the valency or the N factor. So here N factor is your valency, but it is the charge on your ion. Any doubt in this formula? Is this mathematical equation clear to you? So you must know the terms also. Okay, terms are very important here. W you already know, it is the amount of metal which is deposited on your given electrode or the amount of gas which is liberated. I is the amount of current you have supplied, and T is the time for which your current is supplied, and Z is the electrochemical equivalent. So Z is written as equivalent weight by 96500, and equivalent weight is equals to atomic weight by valency. Is it clear to all of you? Any doubt in this? Suppose I say that you have to calculate the Z value for Na plus. So can you just please calculate it and write it in the comment section? Calculate the Z value, means your electrochemical equivalent for Na plus. So what will be the value of Z there? You can just try to use your calculator so that calculation can be easier for now. Just post it in the comment section, the value of Z for Na plus. Meanwhile, if you have a doubt, you can also post it here. So I'm waiting for a while. What will be the value of Z for Na plus? The formulas are in front of you, and I hope it is very easy to solve. So what will be the value of Z for Na plus? Anyone who got the answer? So first of all, calculate the equivalent weight, which is simply atomic weight by valency, and then you calculate equivalent electrochemical equivalent by dividing your equivalent weight by 96500. Anyone who got the answer for this? What will be the equivalent weight of Na plus? Okay, so Varsha Khare is telling it as 2.3 into 10 to the power minus 4. Anyone else? What will be the equivalent weight of Na plus? Okay, so surely you will take 23, right? Because 23 is the atomic weight of your sodium. Then you divide the atomic weight of sodium by its valency. Since I am telling it as Na plus, so the valency will be 1 for Na plus. Therefore, your equivalent weight will be 23. Then further, if you divide 23 by 96500, what you will get? You will get it as 2.383 into 10 to the power minus 4. Okay. Yes, very good. VK. Now, let us move forward. Now, I will give you a different form of this same formula that we saw right now. It's very simple. So, first of all, you should know that what is this 96500? It is basically the charge due to 1 mole of an electron. How you will find it? It's very simple. So, charge on 1 electron is 1.6 into 10 to the power minus 19. Therefore, the charge due to 1 mole of electron will be 1.6 into 10 to the power minus 19 into 6.022 into 10 to the power 23, which is your Avogadro constant. Okay. So, since unitary method is used here, you can easily calculate the charge and you will get it as 96500. See, the calculations are given here. So, this is the approximate value. Okay. You will get it something like 964. Okay. You can just convert into approximate value 96500. Next, number of gram equivalents is equals to number of Faradays of electricity which you are supplying. So, the other form of Faraday's law can be written as W is equals to Z into Q or E by F. So, what are we doing here? We are writing here equivalent weight by F. Then further, what is E? How can we calculate E here? So, E is simply the molar mass by valency. So, we have just included our previous formula in this given formula to get our final form, which is W is equals to I into T into M by F into N. Here, M is the atomic weight, F is the Faraday's constant, N is the valency. Now, moving on to the next part, which is Faraday's second law of electrolysis. So, what is Faraday's second law of electrolysis? It states that for a given amount of electricity supplied during electrolysis, the number of equivalents of the substance produced is same. If we take different container, then by using the same amount of electricity during the electrolysis, the number of equivalents of the substance produced in each container will be equal. Okay. Remember, this container should be connected in series form. Now, how do we write it? So, W is A by WB is equals to EA by EB. So, these are the two species. You can take it for multiple species as well. Here, what is WA? WA is the mass deposited due to substance A. So, we are taking two substance A and B, and we supplied electricity through both of them and the same amount of electricity. Then their equivalence, electrochemical equivalence is same. Therefore, you can say that WA by WB is equals to EA by EB. Then next, EA is the equivalent weight of A. Then WB is the deposited mass of substance B, and your EB is the equivalent weight of substance B. Now, you will get a good grasp of this formula if you try numerical problems onto it. So, I will try to explain the same when we will do questions on it. Okay. But still, what I am saying here is that if you are supplying the same amount of electricity, then the equivalent, electrochemical equivalent is same for both the substances that you are taking, irrespective of the nature of these two substances that you are considering. So, we are writing here it as WA by WB is equals to EA by EB. Okay. I hope this part is clear to you. If not, we will try to understand the same with the help of a question. Next, we have Kohlrausch's law. So, this is the last part of the theory that we will discuss. Then after, we will do questions for the same. It states that molar conductance at infinite dilution means your limiting molar conductance. So, it is talking about limiting molar conductance. So, for an electrolyte is equals to the sum of the ionic conductance of its constituents ion, meaning that the contribution of anion and cation is added and both are added together to give the complete molar conductance. Now, how do we calculate it? It's very simple. So, basically the formula is lambda naught m is equals to x into lambda naught A plus Y lambda naught C. What is lambda naught A here? You can see that we have a lambda naught A here. It is the limiting molar conductivity of your anion, and lambda naught C is the limiting molar conductivity of your cation. What is X and Y? X and Y are the stoichiometric coefficient. Now I will try to explain the same with the help of a proper example. Suppose if I take acetic acid, if I dissociate this acetic acid into ion, it will give you acetate ion and H plus. So these are the two ions you will get. Got it? And what will be the count of both? Of course, it will be 1. So 1 mole of your acetic acid will give us 1 mole of acetate ion and 1 mole of H plus. Now, the total molar conductivity, limiting molar conductivity of acetic acid is simply the contribution from both the ions, which is your cation, acetate ion, and anion, which is your acetate ion, and cation, which is your proton. Got it? Now let me take a different example where the stoichiometric coefficient is not 1. So here the stoichiometric coefficient is 1. So we don't need to multiply it with a certain number. But here if you take the example of Al2SO4 whole thrice, we can clearly see from the formula we have 2 moles of aluminium and 3 moles of sulfate ion. So if you want to find out the limiting molar conductivity of this whole species, you have to take contributions from both. So how we will calculate it? So we will first of all write the limiting molar conductivity of Al3 plus, and since 2 of them are present here, we have to multiply it with 2. Similarly, if I take it for sulfate ion, we have 3 moles of sulfate ion present here, so you have to multiply it by 3. Got it? So in this way, you will calculate it for respective compound, and it will totally depend upon the stoichiometric coefficient, that what value you will get. Is it clear to all of you? Now, it can only be used to calculate limiting molar conductivity and not any molar conductivity. Got it? Are you getting my point here? This is applicable to both weak and a strong electrolyte, and you can see a quick example of it, but it can only be used to calculate the limiting molar conductivity and not the molar conductivity at any concentration. Any doubt in this? And we use it for the same purpose also. So we have already seen a way to calculate the limiting molar conductivity for strong electrolytes, but we don't know that how do we calculate it for weak electrolytes. So for that case, we use this Kohlrausch law. Okay, and you will see questions which are based upon this principle only. So you are given with the molar conductivity, limiting molar conductivity of some strong electrolytes, and then you have to do certain arithmetic calculation so that you can get it for a weak electrolyte by considering their ions. Okay, so rather than doing a complete practical situation, taking a complete practical situation, we use the values of your molar conductivity of ions from strong electrolytes, and then we add them together to find it for weak electrolytes. Is it clear to all of you? Anyone who has a doubt in this part, you can just ask it here. Now we will move on to the last part, which is application of this Kohlrausch law. Why it is used. So one of the application is already told by me. It is used for calculating the limiting molar conductivity of weak electrolytes. Any doubt till this point? If you have a doubt, you can just please post it here, or we can move forward. Okay, so let us move forward onto the last part of this application of Kohlrausch law. So, first of all, as I said, it is used to calculate the molar conductivity at infinite dilution, or I would say the limiting molar conductivity of weak electrolytes. Second, it is used to calculate the degree of dissociation, and this formula that you are seeing right now is very, very important. It is alpha is equals to lambda c by lambda naught c, lambda naught m. Now this is same as your lambda naught m. Either you can write it as lambda naught m or lambda infinity m. Both are same. It is limiting molar conductivity at infinite dilution or limiting molar conductivity. Both are same terms. What did I say? Again, I am repeating my point. It's very, very important. So you can get confused here. So molar conductance at infinite dilution or limiting molar conductance, both are same. Got it? Now there is a relation between molar conductance at a given concentration and molar conductance at infinite dilution. So if you want to find the degree of dissociation value for a particular concentration, you will calculate it as alpha is equals to lambda Cm by lambda naught m, where lambda Cm is the molar conductance at given concentration and lambda naught m is the molar conductance at infinite dilution. Now moving on to the next law, to the next application, which is it's used to calculate the acid dissociation constant, or for base it can be used to calculate the base dissociation constant. How it is used? So from the previous formula you can get your alpha and you already know what is your concentration. So you can just simply plot it here or use it here to calculate your dissociation constant easily, and this is asked in your question, in your examination as well. So you will be given with your value of your lambda Cm and lambda naught m, and then you can be asked to calculate the dissociation constant at a particular concentration. So first you will calculate your alpha, then you can use it to calculate your equilibrium constant or your equilibrium dissociation constant. Is it clear to you? So this is very, very important. And the last part is your determination of solubility of sparingly soluble salt. So in our ionic equilibrium, we talked about this sparingly soluble salt. These are those salts which are partially soluble or soluble to a very less extent in a given solution. Okay. And for that, we can calculate solubility, which is simply the maximum concentration which is possible for that sparingly soluble salt. Okay. Solubility is nothing but the maximum concentration of that particular sparingly soluble salt, and it is given as kappa into 1000 by lambda naught m. I hope this is clear to you. Anyone who has a doubt till this part? So we move on to questions. So if you have a doubt, you can just post it here. Next we'll start questions which will be PYQs on the same topic. So I assume that it is clear to all of you. Now next we will see the question part. So this is your first question. You are given that conductance is directly proportional to area of the vessel and the concentration of the solution in it, and is inversely proportional to length of the vessel. So everything is given itself in the question. You have to decide the unit of constant of proportionality. Okay. So 4 options are given here: Simon meter per mole, second Simon meter square per mole, third Simon per square, then we have meter square mole, then Simon square meter square per mole square. So what you have to do, you have to find the unit for conductance. Okay. So if you know it, if you know the formula, you can just quickly know it from the formula itself, or it is provided in the question as well. Okay. So the information is well versed in the question. So it is directly proportional to area of the vessel, means you have to take the unit of area, which is centimeter square, in the numerator. Then it is directly proportional to concentration. Remember, if you are taking your area in meter square, you have to take the concentration also in mole per meter cube. Okay. Then and then only you can find a specific unit for it. Since for calculation you have to keep the same unit, so for concentration you will take mole per meter cube. Then in the denominator you will put the unit of length, since it is inversely proportional to length, so it will be per meter. So meter square multiplied by mole per meter cube divided by divided by meter. So just try to find out what will be the correct unit for it. And if you got an answer, please comment it here in the comment section. Anyone who got the answer for this question? So what will be the answer for this question? Okay, so I'm seeing an answer as B. So let us move on to the answer. The correct answer will be B, which is Simon meter square per mole. How do we find it? So it is given in the question as well. And you know it also. What will be the formula for conductant? It is kappa into area into concentration by length. Okay. Now, next, if you just arrange it for kappa, it will be kappa is equals to conductance into length by area into concentration. Then we'll put the units here. So kappa is equals to Simon into meter, then divide by meter square into mole per meter cube. Okay. So we are removing the proportionality constant and we are getting conductance here. So this was the part that is not given in the question. So for that you have to you need to remember the formula as well. Just cancel out the units here. So meter, then we have meter square in the denominator and per meter cube. Next, this unit will be cancelled out. Meter will be meter square will be written here, and per mole. Since mole is a denominator, if you put it in the numerator, it will be per mole. Then Simon meter square per mole. Okay. Next question. Given that resistance of a 0.2 mole solution of an electrolyte is 50 ohm, then next thing which is mentioned is specific conductance is 1.3 Simon per meter. After that, you have to calculate the molar conductivity if the resistance for 0.4 molar of the same electrolyte is 260 ohm. So two conditions are given here. Okay. In the first condition, you are given with the resistance, then concentration and the specific conductance. In the second condition, the resistance is given, the concentration is given, but you have to find the molar conductivity. How you will do it? So the main hint for this question would be that since you are taking the same thing, okay, same electrolyte, therefore the L by A value will be same. Okay, we'll use that thing to solve it. First of all, you must know that what is the relation between specific conductance and resistance. So specific conductance is 1 by G, 1 by 1 by rho. Okay. I hope I've given even much hint for this question. Just try it by yourself and try to calculate the molar conductivity. So lambda m is equals to kappa into 1000 by C. Okay, you will use that same formula. So C is given here. First you have to find the kappa. Anyone who got the answer? So remember the formula, R is equals to rho L by A. Okay. So rho can be calculated from the specific conductance. It will be 1 by 1.3. From there you can get the value of L by A. Then you can put it here and then calculate the kappa. And finally you can use it to calculate the lambda m, which is kappa into 1000 by C. Remember, you can do a mistake here because all of them are having the same value on the numerical term. Okay, 625 is written multiple times. So take care of the units. Okay, it's very important here. Okay, so I'm moving on to the solution. If you get it, you can just post it here meanwhile. So first of all, the answer will be B, which is 6.25 into 10 to the power minus 4 Simon meter square per mole. Then, how you will solve it? First of all, what is the relation between specific conductance and molar conductivity? It is specific conductance is equals to conductance into cell constant. Now, next, what is given here? You have the values of your resistance, so you can write it as 1 by 50. Then you can find the cell constant from here, as I said earlier. So if you just calculate it, you will get it as 65 per meter. So why are we getting it as per meter? Because L by A means meter by meter square. So that will give you per meter. Now, as I said earlier, it will remain constant, but you need to convert it into centimeter as all the units are in centimeter. So what will be done here? You have to divide this thing by 100 to get it in centimeter. Now, we will use the formula of molar conductivity, which is lambda is equals to kappa into 1000 by C. Okay. So just put the values here. So kappa can be calculated right here. So it will be 1 by R into cell constant or G into cell constant. Okay. So 1 by 260 into 65 by 100 and 1000 by 0.4. Okay. Now, next, if we just calculate this, you will get it as 6.25 Simon centimeter square per mole. If you are not getting the right value, no issues here. You have to further convert it into meter. Okay, then and then only you will get your correct answer. So if you have done a mistake, it's a very silly mistake. Take care of it. The unit conversions are very, very important because answers were given in SI unit. So what we have to do, you have to convert this centimeter square into meter square, and for that you have to multiply it with the 10 to the power minus 4 because 1 meter is equals to 100 centimeter. Therefore, 1 centimeter is equals to 10 to the power minus 2 meter, and since centimeter square is given here, so we will use 10 to the power minus 4, which is 10 to the power minus 2 square times. Next question. So question number 3. The resistance of a 0.2 molar solution of an electrolyte is 50 ohm. Then the specific conductance of the solution is given as 1.4 Simon per meter. If the resistance of 0.5 molar solution of the same electrolyte is 280 ohm, the molar conductivity of 0.5 molar solution of that electrolyte in Simon meter square per mole is. So this is a similar kind of question. Okay, just try to solve it by yourself, and if you give it in the comment section, what will be the answer for this question? So what is given in the question? You are given with a certain concentration, okay, and resistance at that concentration. Then you are given with the specific conductance, okay. Now next, you are given with the second condition, which involves the concentration as 0.5 molar and the resistance at that point as 280 ohm. Okay. Now first you try to find the L by A value from there, put it here, and then you further plot it in the third condition, second condition, and try to find the molar conductivity at that. Means it is similar to the previous question, almost similar. Let's try to solve it. 4 options are given here again. Be careful with the units. So you have to find the answer in Simon meter square per mole, and the options are 5 into 10 to the power minus 4, 5 into 10 to the power minus 3, 5 into 10 to the power 3, and 5 into 10 to the power 2. Okay, so let us move on to the solution. First of all, the correct answer will be A, which is 5 into 10 to the power minus 4. Then, how you will solve it? The things which are given here are specific conductance 1.4 Simon per meter and your resistance, which is 50 ohm. If you put this into the equation, R is equals to rho L by A, or kappa is equals to 1 by R into G star, which is simply your L by A, which is represented by the cell constant G star. Next, put the values here. Kappa is given 1.4. 1 by R means 1 by 50 multiplied by G star. Why are we keeping the G star same in both the conditions? Because it is given here that your electrolyte is same. That is the reason we are taking the same L by A value. Next, you will find that your G star value is 70 per meter, or if you convert it into centimeter, you have to simply divide this thing by 100. It will give you 0.7 per centimeter. Next, we will use this L by A value to calculate our molar conductivity. So we got our G star as 0.7 per centimeter and your resistance is given for the second condition as 280 ohm. So how do you calculate the specific conductance? So kappa is given as 1 by R into G star, or you can simply write it as G into G star. So 1 by 280 into G star, which is 0.7, it will give you 0.0025 Simon per centimeter. Lastly, you can use this kappa value to calculate your lambda m by using the formula lambda m is equals to kappa into 1000 by C or M, where C or M is the molar concentration. Next, if you put the value of kappa here, which is 0.0025 into 1000, why are you multiplying it by 1000? Because you need to convert your unit from decimeter cube to centimeter cube. Okay, you will get it as 5 per ohm centimeter square per mole, but you should find the answer in Simon meter square per mole. For that reason, you need to convert it into meter square. How you will do it? It's very simple. Simply multiply this whole thing by 10 to the power minus 4, because 1 centimeter, again that same thing, 1 centimeter is equals to 100 meter, therefore 1 meter is equals to 100 centimeter, therefore 1 centimeter is equals to 100 raised to the power minus 1 meter. Got it? Okay. Now this will be the last question of today's class, and it is given that the equivalent conductance of NaCl at concentration C and at infinite dilution are lambda C equivalent and lambda not equivalent respectively. The correct relation between both of them will be. So we have seen a formula for the same, but that was in terms of molar conductivity. But no issue, you can apply that same thing here. The formula will not change at all. Only in place of lambda m and lambda not m, or I would say lambda cm or lambda not lambda infinity m, you will write it here in terms of equivalence rather than writing in terms of molar. Okay, so lambda c equivalent is equals to lambda infinite equivalence plus bc, first option, minus bc minus b root c and plus b root c. So only the last part is changing, and you have to decide that which is the correct operation to do. Remember, we talked there that this is applicable to strong electrolyte, and always there will be a decrease in value of your lambda m or your lambda c equivalent in this case if you increase the concentration. Therefore, there should be a negative term, because on increasing the concentration, this value is decreasing. Next, the variation was not that much large, it was of small content, therefore you have to take the root of the concentration. So this is the logic to learn this. Okay, this is not actual thing, I'm simply just trying to rationalize the formula so that you can easily learn it. As I said earlier, that this variation with concentration was not that much significant, so you have to take the root value, a lesser value of the concentration. So from that point of view, your correct answer will be option number C. Okay, so C will be your correct answer, and it's a direct equation type question. There is nothing much to discuss about it, you know it very well. It is a Debye-Huckel-Onsager equation, but here we are taking it in terms of equivalent conductance rather than molar conductance. Okay, so here lambda C equivalent is your equivalent conductivity at concentration C. Then your lambda infinity equivalent is your limiting equivalent conductivity at infinite dilution. Next, we have C as your concentration. So this was all for today's class. Thank you for joining the session. I hope you enjoyed it. So if you have a doubt right now, you can just post it here. Okay. So in few minutes, our maths faculty will join you. Just wait for a while.
Hello everyone. So welcome to Crash Course. So today we will discuss application of derivative. So at first, let's do trend analysis for chapter application of derivative. So according to last 8 year, the chapter weightage of application of derivative for JEE mains examination is 4.26%. Okay. And according to year wise data, so in the year 2024, one question came from the topic maxima and minima of average type. In the year 2023, again one question came from the topic maxima and minima of average type. In the year 2022 and 2021, two questions in the year 2022 and one question came from the topic increasing and decreasing function of average type. And from the year 2020 to 2017, question came from the topic maxima and minima of average and difficult type. Okay. So in today's class, at first we will understand derivative as a rate of change. So what is the relation between derivative and rate of change? Then what is increasing function, its definition, and how we can relate increasing function with derivative of a function. After that, decreasing function, what is monotonic function, then tangent and normal to a curve. After that, we will discuss angle of intersection of two curves. So if we have two curves, then how we can calculate angle of intersection of these two curves using the derivative. Okay. Orthogonal curves, and at the last we will discuss theorems, Rolle's theorem and Lagrange mean value theorem. Okay. So let's start. So derivative as the rate of change. So we already familiar with dy by dx, that is differentiation of y with respect to x. So what does it mean? So dy by dx is nothing but rate of change of y relative to x. Dy by dx represent change of y with respect to x. Let's suppose y is a variable quantity and it depend upon time, that is y is a function of t, that is y is equal to ft. So when we change, there is a small change in del t, then y is also change. With the change in del t, corresponding change in y del y. So if we take del t as a change in t, then corresponding change del y in y, then average rate is given by del y by del t. That is your average rate of change. From this figure, here y is equal to ft is your function and y depend upon t. y2 minus y1 is change in y with respect to time, as time change from t1 to t2, that is del t is equal to t2 minus t1, then there is corresponding change in y, that is y2 minus y1, and that average rate of change is given by y2 minus y1 by t2 minus t1. Okay. So if you want to find the instantaneous change in this rate, so when we apply limit del t tending to 0, that is rate of change in t tending to 0, there is very small change in t, approximately 0, then the rate of change become instantaneous. And now this rate of change, instantaneous change, is given by dy by dt. So when limit del t tending to 0, then your rate of change, that is average rate of change, del y by del t, is equal to dy by dt, the differentiation of y with respect to t. So dy by dt is rate of change of y with instant t. This is your instantaneous change of in y with t. Okay, clear? Now dy by dt, that is rate of change in y with t, is positive if y increases as t increases, and it is negative if y decreases as t increases. So if it given that dy by dt is equal to plus 3, it means as t increases, y is also increases with the rate of 3. And if it is negative, it means as t increases, y is decreases with that rate. Okay. So according to the sign of dy dt, we know, is it the y is increases with t or is it decreases with t? Now let's understand what is increasing function. So if you have a function f and that function is defined on on AB, then function f is said to be increasing function if, what is the definition? If x2 is greater than x1, then it imply the function value fx1 is less than equal to fx2 for all x1 x2 belong to this open interval AB. So if we take any 2 point from AB and there is a relation between that point is x1 is less than equal to x2, then if it imply the value of function at x1 is also less than equal to the value of function at x2, then that function is increasing function. As the value of x increase, the function value is also increases. Clear? We can relate this the definition of increasing function by derivative. So if fx is, the function fx is increasing if derivative of f, the first derivative f prime x, is greater than equal to 0. So if you differentiate that function and we get that is greater than equal to 0, then that function fx is increasing function. And the function fx is strictly increasing if f prime x is greater than 0. Clear? So if we have a function fx and the function is continuous in closed interval AB and differentiable in open interval AB, then fx is an increasing function in closed interval AB if f prime x greater than equal to 0 in open AB. So if we calculate first order derivative of fx, that is f dash x, and we get that function is greater than equal to 0 in that open interval AB, then your function fx is an increasing function. And if we get f dash x is greater than 0, equality sign is removed in the open interval AB, then your function fx is strictly increasing function. Clear? This is your figure of increasing function and strictly increasing function. So what is the difference between increasing and strictly increasing function? It might be possible in increasing function, if x1 is less than equal to x2, it may be possible that fx1 is equal to fx2. But in a strictly increasing function, if x1 is less than equal to x1 is less than x2, then fx1 must be less than fx2. Okay, then that function is strictly increasing function. Clear? Now we will discuss what is decreasing function. So a function f is said to be decreasing function in open interval AB if, definition of decreasing function, if we take x1 less than x2 and it imply the function value fx1 is greater than equal to fx2 for all x1 x2 belongs to open interval AB, then function f is decreasing function. That means if we take increasing x1, x2, that is x1 is less than x2, and we get function value of fx1 is less than greater than equal to fx2, that is function values decreases, then that function is called decreasing function. And according to derivative, fx is decreasing, fx is known as decreasing if f dash x less than equal to 0, it is strictly decreasing if f dash x less than 0, less than 0. So if we have any function fx that is continuous in closed interval ab and differentiable in open interval ab, then that function fx is an decreasing function in interval ab if for f prime x less than equal to 0 in open interval ab, and it is strictly decreasing function in interval ab if f prime x less than 0 in open ab. Clear? So now if we have any function and we want to prove is it a function increasing or decreasing, we can check by the f prime x. If we get f prime x is greater than equal to 0 in that interval, then your function is increasing function, and if you get less than equal to 0, then your function is decreasing function. And if you remove the equality sign, then your function is strictly increasing and strictly decreasing. Clear? First figure represent your decreasing function, and second figure is your strictly decreasing function. Clear? Now, what is monotonic function? So, if a function f is either increasing or decreasing in that interval, then function is monotonic on interval. Clear? Simple definition. Okay, result on monotonic function. There is some result. First one, if fx is a strictly increasing function on interval ab, then f inverse exists and it is also a strictly increasing function. So if we have any function fx and that function it is strictly increasing on interval ab, that means f prime x is greater than equal to 0, then it implies f inverse is also exist, and that function f inverse is also a strictly increasing function. So if f is a strictly increasing function, then f inverse is also a strictly increasing function. Second one, now if your function f is strictly increasing on interval ab such that it is continuous, now there is two condition, strictly increasing plus continuous, then it imply f inverse is also continuous on which interval? The interval is now fa to fv, the function value of eta a and b. So interval is changed. Fx is strictly increasing and continuous on the interval ab, but f inverse is continuous on interval fa to fb. Third, fx is continuous on ab. This is a definition of monotonic increasing. That is, if a function is continuous on a closed interval ab and the first derivative, that is f prime c greater than equal to 0 for each c belongs to that open interval, then fx is monotonic increasing on ab. And for decreasing, for monotonically decreasing, fx is continuous on ab, and if f prime c less than equal to 0 for all c belongs to that open interval, okay, open interval ab, then your function fx is monotonically decreasing on close ab. Clear? Now we will discuss what is tangent and normal to a curve. So how we define a tangent? So if we have any function, let's suppose y is equal to fx, then we draw a curve. So tangent is a line that touch the curve at only at one point. at a single point. So from this figure, that line AP that touches the curve at a single point P, so this is your tangent. Okay, so we just draw a tangent to the curve y is equal to fx at a point P x1 comma y1. Clear? And when we draw this tangent cut the x-axis at a point A and it make an angle psi with positive x direction. Clear? So AP is the tangent to the curve y is equal to fx at the point P is equal to x1 comma y1 that touch the curve at a single point at a P and it make an angle psi with positive x direction. Clear? And what about normal? So when we draw a perpendicular to the tangent at a point P, then that line which cut the x-axis at B, so PB is your normal to the tangent of a curve y is equal to fx at a point P x1 comma y1. Clear? First formula for tangent. The slope of this tangent is given by derivative dy by dx at a point x1 comma y1. So when we differentiate function y is equal to fx with respect to x, we get dy by dx, and at a particular point x1 comma y1, it gives you slope of that tangent, that is tan psi. So slope of tangent, that is tan psi, is equal to dy by dx at a point x1 comma y1. We can also write equation of tangent by using the point x1 comma y1 from where the tangent is passes touch the curve, and as we know the slope of the tangent is dy by dx at x1 comma y1. So equation of tangent is given by point slope form, that is y minus y1 is equal to dy by dx at x1 y1 x minus x1. Clear? Because we can give an equation of a straight line when we know any point on the line and slope of the line. So point slope form is y minus y1 is equal to dy by dx at x1 comma y1 into x minus x1. Length of tangent. So length of tangent, that is PA. So PA is equal to y1 cosec psi. We can easily calculate this as it makes a right angle triangle. So by using trigonometry, PA is equal to y1 cos psi, and we can find the cos psi in terms of dy by dx x1 y1, as tan psi is equal to dy by dx at x1 y1. So we can find cosec psi in terms of dy by dx at x1 y1. So what is the formula for length of tangent? That is equal to mod y1 numerator root under 1 plus dy by dx at x1 y1 square by dy by dx at x1 y1. So by using this formula, we can find the length PA, that is length of tangent. Clear? Next, length of subtangent, that is AC. AC is your subtangent. So this length is calculated by y1 cot psi, that is equal to mod y1 dy by dx at x1 y1. Clear? So these are the formula related to tangent. Now for normal. So what is normal? So normal to a curve at a point P x1 y1 is a line perpendicular to tangent at P and passing through P. So when we draw a line that is perpendicular to tangent, that's make an angle 90 degree with the tangent, that line is normal to the point P x1 y1. Okay, so PB is perpendicular to the tangent AP. So we can find slope of this normal, because as this normal is perpendicular to the tangent, And we know when two lines are perpendicular, there is a relation between their slopes. So slope of the normal is negative reciprocal of slope of tangent, that is minus 1 by dy by dx at a point x1 comma y1. This is slope of normal. Clear? And equation of normal, again we apply point law form, that is y minus y1. The normal is passes through a point p x1 comma y1, and the slope of normal is minus 1 by dy by dx at x1 comma y1. So equation of normal is y minus y1 is equal to minus 1 by dy by dx at x1 comma y1 x minus x1. And length of normal, that is pb, is given by y1 sec psi, and when we write the sec psi in terms of dy by dx at x1 y1, that is equal to 10 psi, so we get mod y1 root under 1 plus dy by dx x1 y1 whole square. Okay, because we can write sec psi in terms of 10 psi as in by this example, by this formula. This is a trigonometric identity. So what is length of subnormal? That is BC. So BC is given by y1 10 psi, that is mod y1 dy by dx x1 y1. Okay. So here PA is tangent, that is drawn to the curve at a point P x1 y1, and when we draw a perpendicular to this tangent, we get a normal to the curve at a point P x1 y1, and psi is the angle that tangent makes with positive direction of x-axis. Clear? So these are the all formula related to tangent and normal. Clear? Okay. So next is angle of intersection of two curves. So how we can calculate angle of intersection of two curves? So if we have two curves and we want to find what is the angle between them, so what we do, we just draw their tangent at that point of intersection. So at the point of intersection, we draw tangent for first curve and tangent for second curve, and then find angle between this tangent. Okay. So let's suppose we have two curve, y is equal to fx and y is equal to gx, and we need to find angle of intersection between these two curve, and that is equal to angle between the tangent of these two curves. So from this figure, we have two curve, y is equal to fx and y is equal to gx, that intersect at a point P, and we need to find angle of intersection of these two curve. So at first, draw the tangent at a point P for both curves. So first tangent is for y is equal to fx. So it just draw a tangent at a point P for y is equal to fx that cuts x-axis at t1 and make an angle psi 1 with positive x direction, and then draw the second tangent for the graph y is equal to gx that passes through a point P that makes an angle psi 2 with positive x direction and cuts the x-axis at point t2. So pt1 is tangent for a curve y is equal to fx at a point P, and pt2 is the tangent to the curve y is equal to gx at the point P, and angle between this tangent is phi. So we need to find phi. Phi is the angle of intersection of these two curves, and that is equal to angle of intersection between the tangent pt1 and pt2. Okay. Now we can find the slope of this tangent, that is given by dy by dx. So for tangent 1, we calculate the slope of tangent 1, that is dy by dx at 1 at a point x1 comma y1, coordinate of P, that is x1 comma y1, and slope of tangent 2, that is pt2, is given by dy by dx 2 at a point x1 comma y1. So we can calculate this angle phi by using the relation tan phi is equal to mod dy by dx at x1 y1 for that is slope of tangent 1 minus slope of tangent 2 that is dy by dx 2 at x1 y1 by 1 plus dy by dx slope of tangent 1 at x1 y1 and dy by dx that is slope of tangent 2 x1 y1. So if we consider slope of first tangent as m1, that is slope of that is tangent of for curve y is equal to fx, we consider the slope of tangent is m1, and for the tangent pt2 we just consider its slope is m2. Then tan phi is given by mod m1 minus m2 by 1 plus m1 into m2. So by using this formula we can calculate angle of intersection of two curves. Simple idea is to find the angle, we just draw the tangent at the point of intersection for both curve and we find the angle between them, angle between the tangent, and that is equal to angle between the curves. Clear? Now next is orthogonal curves. So if there are two curves, let's suppose y is equal to fx and y is equal to gx, and the angle of intersection between these two curves is right angle, that means they intersect at 90°, then these curves are called orthogonal curves. That is, if the angle of intersection of two curves is a right angle, the two curves are said to intersect orthogonally and the curves are called orthogonal curves. So when the angle is 90°, that is phi is equal to pi by 2. So when phi is equal to pi by 2, we get from the equation of tan phi that is given in the previous slide, that is tan phi is equal to mod m1 minus m2 by 1 plus m1 into m2. So when phi is equal to pi by 2, it implies m1 into m2 is equal to minus 1. So when the product of slope of this both tangent is minus 1, then curves are orthogonal. Okay, that is slope of first tangent dy by dx 1 and slope of second tangent for the second curve dy by dx 2 is equal to minus 1, then your curve is orthogonal curves. And one important note, two curves touch each other if m1 is equal to m2. If slope of the tangent of first curve is equal to m1 and slope of for the second curve is m2 for the tangent and both are equal, that is m1 equal to m2, then two curves touch each other. Okay. So now we will discuss important theorems. First one is Rolle's theorem. So what is the statement of Rolle's theorem? So let f be a real valued function and this function is defined on a closed interval ab such that there is some condition for Rolle's theorem. First one is the function fx is continuous in closed interval ab. Second condition, fx is differentiable in open interval ab. And third condition is fa is equal to fb. These are the conditions for Rolle's theorem. If you define a function f, that is a real valued function, and that is defined a closed interval ab, and if you satisfy certain property, that is first one is fx is continuous in closed interval ab, fx is differentiable in open interval ab, and third one is fa is equal to fb, that is function value of at a and b is equal, then there is some point c in the open interval ab such that f dash c is equal to 0. and this is your Rolle's theorem. Okay, so if any function that is defined in closed interval AB and satisfy this three condition, that is continuous on that closed interval AB, differentiable in open interval AB, and the function value at the end point are equal, that is f is equal to fb, then there must be some point C on that open interval AB where the first derivative at that point C is 0, that is f prime C is equal to 0. To understand this geometrically, so let's suppose we have a function y is equal to fx and we satisfy all these three condition. For the first figure, fx, the function is continuous in the interval closed interval AB, is also differentiable in open interval AB, and the function value at a and b is 0, that is f is equal to 0, fb equal to 0, so equal f is equal to fb equal to 0. Then according to Rolle's theorem, there must exist a point C, that is a peak value, so this is C, where the function value is fc. So at a point C comma fc, if we draw the tangent at that point, in which point C comma fc, if we draw the tangent at that point, then that tangent is parallel to x-axis, and that is geometrical meaning of Rolle's theorem. Because as the f dash C is equal to 0, it means the slope is equal to 0. So if slope is equal to 0, it means that line is parallel to horizontal axis, that is x-axis. Clear? So if any function satisfy all the condition of Rolle's theorem, then there must be a point on that curve between that AB, that is when we draw that tangent on that point, that tangent is parallel to x-axis. Clear? It might be possible we get more than one point, that is in the according to the second figure. Here the given function fx is continuous, differentiable, and at a point a and b the function value is same, f is equal to fb. So we get 2 points where the derivative, first derivative f dash is equal to 0, and when we draw the tangent at both points, that tangent is parallel to x-axis. So Rolle's theorem confirms us there must be a point. It can be more than 1 point. Okay. So there is at least 1 point C between AB such that the tangent to the curve at C comma FC is parallel to x-axis, and this is your geometrical meaning of Rolle's theorem. One algebraic interpretation. So if fx is in any polynomial, so between any two roots of this polynomial fx, there is always a root of its derivative f prime x. So what does it mean? So fx is polynomial, and if it has two roots, then let's suppose a and b are the root of this polynomial. So f is equal to 0 and fb is equal to 0. And as it is a polynomial, so it is continuous, it is differentiable on the interval AB. And as f and f is equal to 0, so f is equal to fb, that is equal to 0. So it satisfies all the condition of Rolle's theorem. So according to Rolle's theorem, there must be a point C where f dash, that is f prime C, is equal to 0. Then that C is the root of its derivative f prime x. Clear? Now next theorem, Lagrange mean value theorem. So if f is real valued function, you have a real valued function, and that function is continuous on closed interval AB, first condition, and differentiable in open interval AB, second condition, then there is at least 1 point C in the open interval AB such that f prime C is equal to fb minus fa by b minus a. So what is the statement? If you have a function f, and if that function satisfy first condition as continuous in closed interval AB, second condition differentiable in open interval AB, then there exists at least one point. It can be more than one, but at least one point C on the open interval AB such that f prime C is equal to fb minus fa by b minus a. Okay. Geometrically, for any chord of the curve y is equal to fx, there is a point on the curve where the tangent is parallel to this chord. So this is your geometrical meaning. That is, if you draw a chord on the curve y is equal to fx, then there must be a point on that curve where if you draw a tangent to that point, then that tangent is parallel to that chord. So in the particular case, when we take fa is equal to fb, so just take, according to Rolle's condition, Rolle's theorem, function is continuous in closed interval AB, function is differentiable in open interval AB, then, and third condition is fa is equal to fb. So in mean value theorem, if we add one more condition, that fa is equal to fb, so now this function satisfies all the condition for Rolle's theorem. So then this expression fb minus fa by b minus a becomes 0 because fa is equal to fb. So we get f prime c is equal to 0 for some c in open interval AB. Thus, Rolle's theorem is just a particular case of mean value theorem. So if a mean value theorem, if we add one more condition, that is fa is equal to fb, then mean value theorem is just a Rolle's theorem. Clear? So from this figure we can understand the geometrical meaning of the Lagrange mean theorem. So if we have a function f y is equal to fx, let's suppose, and that function is continuous in closed interval AB, there is a point a and b, so in this interval this function is continuous, and differentiable in open interval AB, that is function is smooth in a to b, then according to mean value theorem there is at least one point C. So there is C and the function value at C is fc, so there is a point C comma fc such that f prime C is equal to fb minus fa by b minus a. So at this point C comma fc, when we draw the tangent at that point, this is parallel to the chord at a point a comma fa and b comma fb, and this is your geometrical meaning. That is, for any chord at point a comma f and b comma fb, if it satisfies the all condition of mean value theorem, there must be a point, at least one point C, where if we draw the tangent at that point, that tangent is parallel to the chord at a point a comma fa and b comma fb. Clear? And slope of that tangent is given by formula fb minus fa by b minus a. So if you can relate by the slope, for the parallel lines slopes are equal, and the slope for the point a comma fa and b comma fb, as it 2 points are given, so slope are given by fb minus fa and b minus a. This is a slope for chord. And what is the slope of the tangent that we drawn at the point C comma fc, according to mean value theorem, is given by first derivative, that is f prime c, that is equal to fb minus fa by b minus a. Clear? So let's summarize the theory of application of derivative. So first thing, what is the meaning of derivative? Rate of change, dy by dx mean rate of change of y with respect to x, and if there is a function y or function of t, that is y is equal to ft, then average rate of change is given by del y by del t, and when we approach del t tending to 0, when you apply the limit del t tending to 0, it converted to dy by dt. Increasing and decreasing function, so if a function f is said to be monotonic function if it is either increasing or decreasing. Tangent and normal to a curve, so for tangent, the slope of the tangent is given by dy by dx at a point x1 comma y1, that is tan psi, and equation of tangent is given by y minus y1 is equal to dy by dx at a point x1 comma y1, x minus x1, and the slope of normal is given by minus 1 by dy by dx at x1 comma y1, and equation of normal is given by y minus y1 is equal to minus 1 by dy by dx at x comma y1, x minus x1. And what is angle of intersection of two curves? That is equal to angle between the tangents. That tangent we drawn at the point of intersection for both curve. And orthogonal curves, when the angle of intersection between two curves is right angle, then that curves are called orthogonal curves. Clear? Next is Rolle's theorem. So what is Rolle's theorem? If f is a real valued function and we define on a closed interval AB such that f is continuous on closed interval AB, f is differentiable in open interval AB, and third condition, if f is equal to fb, then according to Rolle's condition we get a point C on this open interval AB such that f prime C is equal to 0. And second theorem, Lagrange mean value theorem. So if f is a real valued function and it's continuous on closed interval AB, differential in open interval AB, then there exists at least one point C on the open interval AB such that f prime C is equal to fb minus fa by b minus a. Okay. So just wait for a moment. Now we will discuss some question. Okay. So now we will discuss some question. We practice some question related to application of derivative. So first question, if the volume of a sphere is increasing at a constant rate, then the rate at which its radius is increasing is. So in this question we have a sphere, and what is given? The volume of a sphere. So if we consider the volume of a sphere as V, then it is given that is increasing at a constant rate. So V is your volume of a sphere. So the derivative of the volume with respect to time give you rate of change of volume with respect to time, that is dV by dt. And as it is given increasing, so when it is increasing, so dV by dt is positive. So we take a constant k and dV by dt is equal to k. This is given, that is volume of a sphere is increasing at a constant rate. So we can take dV by dt is equal to k. Then the rate at which its radius is increasing. So question is, we have to find what is the rate at which radius is increasing. So we have to find if we consider radius as r, then what is dr by dt? Clear? Options are a constant. Option B, proportional to the radius. It means rate of change of radius is depend upon radius. Inversely proportional to the radius. It means it's depend upon radius but inversely. Option D, inversely proportional to the surface area. Surface area of sphere. Okay. So there is only one information, that is dV by dt is increasing at a constant rate. Okay. So try this. Use the formula for volume of sphere and volume of surface area. And also that is what is given dV by dt, rate of change of volume with time is increasing at a constant rate. So use this information. Okay, let's solve together. Correct option is inversely proportional to the surface area. Okay. So what is given? Volume of sphere is increasing at a constant rate. So if we consider V as the volume of this sphere, then dV by dt, that is rate of change of volume with time, is equal to K, constant. Okay. And we know that the volume of a sphere is given by the formula 4 by 3 pi r cube, where r is the radius of the sphere. So now we can find dV by dt in terms of r. Just differentiate this formula with respect to time. So dV by dt is equal to, now to differentiate right hand side with respect to time, we apply the chain rule. And according to chain rule, we get 4 by 3 pi and differentiation of r with respect to r, that is 3r square into differentiation of r with respect to time according to chain rule. So we get dV by dt is equal to 4 pi r square dr by dt. Clear? So dr by dt is equal to, now just substitute k in place of dV by dt. So we get dr by dt is equal to k by 4 pi r square. Clear? Now what is the formula of surface area of the sphere? Formula for surface area of the sphere is 4 pi r square. So we get dr by dt, that is rate of change of radius with time, is equal to k by 4 pi r square, that is k by surface area of the sphere. And as the surface area is in the denominator, so rate of increasing radius is inversely proportional to the surface area. If surface area decreases, radius increases. If surface area increases, radius decreases. That is the meaning of inversely proportional. Clear? Simple question. Any doubt? Okay, so let's move to the next question. Question number 2. Moving along the x-axis, there are 2 points with x is equal to 10 plus 60 and x is equal to 3 plus t square. Okay, the speed with which they are reaching from each other at the time of encounter is, x is in centimeter and t is in second. So in this question there are 2 points and they are moving on the x-axis. So let's suppose this 2 point A and B. So A and B are moving along the x-axis and the point of position are given by the x is equal to 10 plus 60. So for point A, position is x is equal to 10 plus 60. So position, and for point B is it x is equal to 3 plus t square. So position of point depend upon the time. As time increases, the position of the points are changed. When t is equal to 0, the position of point A is 10 and the position of point B is 3. So when we increase the time, when we increase the value of t, the position of point is also changed. So position is dependent upon time t. Okay, and both the points are moving along the x-axis. Now, second part, the speed with which they are reaching from each other at the time of encounter. So after a certain time they meet. So we, in this question, we are asked for to find the speed with which they are reaching from each other. What is the speed through which they are reaching each other? So when they are cross, what is the speed? What is the relative speed of both the points? Okay, options are 16 centimeter per second, option B 20 centimeter per second, option C 8 centimeter per second, option D 12 centimeter per second. So hint for this question is just use when they are encounter. It means when they are meet with each other, then what is the position for both the point? So when they are meet, the position must be same. That is, position of point A and position of point B both are same, both are equal. So by using this equation, just figure out what is the time, what is the value of t when they are meet each other. Okay, and then we calculate the speed. So if we have the value of if we have the function of position, then we can easily calculate the speed. When you differentiate the position with respect to time, we get the speed. Okay, so just use this formula to solve this problem. Okay, so try. Okay, let's solve. So correct answer is option C, 8 centimeter per second. So when they will encounter, that means when they meet each other, at that point the position of both the points is same. That is 10 plus 60 is equal to 3 plus t square. So when we simplify this equation, we get t square minus 60 minus 7 is equal to 0. And from this equation, we get two value of t. Another value is negative, so we discard the value. We get t is equal to 7. So t is equal to 7. 7 second is the time when this both points meet each other. Okay. So for the first point, to calculate its velocity, we know the position. So when we differentiate the position with respect to time, we get the velocity for the point 1. So v1 is equal to d by dt 10 plus 60, that is differentiation of 10 plus 60 is equal to 6. As differentiation of constant term is 0 and differentiation of 60 is just a 6. So velocity for position first point is 6 centimeter per second. Now at a time 7 second, when a time is 7, for a second point, we calculate its velocity by differentiating with respect to time, by differentiating the position of second point. So d by dt 3 plus t square. So its differentiation is equal to 2t. So at a time 7 second, its speed is 2t is equal to 2 into 7, that is 14 centimeter per second. So at a time 7 second, the velocity of point 1 is 6 centimeter per second and velocity of second point is 14 centimeter per second. But in the question we are asked for relative speed through which they are approaching each other. Okay, and that relative speed, as both velocity is positive, so direction of both the point is same. So to calculate its relative velocity, we just is equal to the difference of the velocity, that is v2 minus v1, 14 minus 6, 8 centimeter per second. So 8 centimeter per second is the speed through which they are approaching each other, or the at the time of encounter, the speed of both point is relative speed is 8 centimeter per second. Clear? Question number 3. An object is moving in the clockwise direction around the unit circle x square plus y square is equal to 1. As it passes through the point 1 by 2, comma root 3 by 2, its y coordinate is decreasing at the rate of 3 unit per second. The rate at which the x coordinate change at this point is. So in this question, there is a circle, there is a unit circle, x square plus y square is equal to 1. It means the circle with center 0, 0 with radius 1. And an object is moving on this circle, on this unit circle, in clockwise direction. Okay. So when this object passes through a point 1 by 2, comma root 3 by 2, at this time, the y coordinate is decreases at the rate of 3 unit per second. Okay, that is dy by dt is 3 unit per second. It decreases, so we get negative rate, that is minus 3. So we are in this question we are asked for the rate at which x coordinate changes. So when the object passes through a point 1 by 2, comma root 3 by 2, its y coordinate changes with its y coordinate is decreasing with rate 3 unit per second. Then what is the rate of change of x? That is what is dx by dt. And options are 2, 3 root 3, root 3, 2 root 3. Okay, so we have to calculate dx by dt. Okay, so let's figure out. Correct answer is 3 root 3. Okay, so what is the equation of given circle? Unit circle, x square plus y square is equal to 1. So when we differentiate this equation with respect to time t, we get, let's apply the chain rule. So when you differentiate x square with respect to time, so first differentiate x square with respect to x, we get 2x, and then into differentiation of x with respect to time, so 2x into dx by dt plus differentiation of y with respect to y, 2y, into differentiation of y with respect to time, dy by dt is equal to differentiation of 1 is 0. So you get x dx by dt plus y dy by dt is equal to 0. Okay. In the question we are asked for dx by dt. We need to find the value of dx by dt. Under information in the question, the object passes through a point 1 by 2 root 3 by 2. So value of x is 1 by 2, value of y is root 3 by 2, and its y coordinate is decreasing at the rate of 3 unit per second. Decreasing, so minus sign, and rate with respect to time, that is dy by dt, y coordinate changes. So dy by dt is equal to minus 3, given information. So at this time we need to find dx by dt, that is rate of change of x coordinate with respect to time. So we need to find dx by dt. So we can substitute this value on our equation. We get 1 by 2 dx by dt plus root 3 by 2 into minus 3 is equal to 0. That is dx by dt is equal to 3 root 3. So rate of change of x with respect to time is 3 root 3. Clear? Any doubt? Okay. Next question. The position of a point in time t is given by x is equal to a plus bt minus ct square, y is equal to at plus bt square. Okay. So these are the position of a point in time t. So these position depend upon time t. According to time, position is also changed. So when time is t, the position x coordinate is x is equal to a plus bt minus ct square and y is equal to at plus bt square. Its acceleration at time t is, then as position is changed with respect to time, there must be a velocity and there must be acceleration. So in this question, question asked for what is acceleration at time t, and options are b minus c, b plus c, 2b minus 2c, 2 into root under b square plus c square. So if we have position of a point, we can calculate its acceleration. Rate of change of position is your velocity, and rate of change of velocity is acceleration. So when we differentiate position two times, first with respect to time first time, then we get velocity, and we again differentiate it, we get its acceleration. Okay. So let's calculate its acceleration. Correct answer is option D, 2 into root under b square plus c square. So given point is x is equal to a plus bt minus ct square and y is equal to at plus bt square. So acceleration in x direction, there is position of point given in two coordinate x and y. So now we calculate acceleration both direction, x direction, y direction, then we combine. So acceleration x direction, just differentiate x with respect to time two times. So when we differentiate x with respect to t, so dx by dt, we get b minus 2ct, and when we again differentiate it, then we get d2x by dt2, that is minus 2c. So this is your acceleration of point in x direction. What about y direction? So position y is equal to at plus bt square. So when we differentiate it with respect to time, dy by dt is equal to a plus 2bt. And when we again differentiate it, so dty by dt2 is equal to 2b. Okay. So resulting acceleration is given by the formula root under d2x by dt2 whole square plus d2y by dt2 whole square, that is root under minus 2c square plus 2b square, that is 2 into root under b square plus c square. Clear? So this is your acceleration for the point. Next question. Water is dripping out from a conical funnel of semi-vertical angle pi by 4 at the uniform rate of 2 centimeters square per second in the surface area. through a tiny hole at the vertex of the bottom. When the slant height is of cone is 4 centimeter, the rate of decrease of the slant height of water is. So there is a conical funnel and water is dripping from this conical funnel through a tiny hole at the vertex of the bottom. Okay, and what is the rate when the water is dripping? With a uniform rate of 2 centimeter square per second in the surface area. The surface area is changed with 2 centimeter square per second when water is dripping. Okay, and the semi-vertical angle of this conical funnel is pi by 4. And specifically the slant height of the cone is 4 centimeter, that is L is equal to 4 centimeter. Then what is the rate of decrease of the slant height of water is? Okay, options are root 2 by 4 pi centimeter per second, 1 by 4 pi centimeter per second, 1 by pi root 2 centimeter per second. None of this. Let's solve it. Correct answer is root 2 by 4 pi centimeter per second. So at first, according to the question, draw the diagram of this conical funnel. So the semi-vertical angle is pi by 4. So this is pi by 4. And let's suppose h is the height of this conical funnel, L is the slant height, and R is the radius. And it is given that when water is dripping, the surface area is changed with uniform rate 2 centimeter square per second. So ds by dt, S is surface area of this conical funnel. So ds by dt is equal to 2 centimeter square per second. What is the formula for surface area of cone? That is pi RL, where R is your radius of this circular base of cone, N is the slant height. Now we can write R in the terms of L and this pi by 4. Okay, so by using a trigonometry, we get pi L, and in place of R, we write L sine pi by 4. What is the value of sine pi by 4? That is 1 by root 2. So we get pi L square by root 2. This is your surface area. Now we calculate rate of change of surface area. So just differentiate surface area with respect to time. So ds by dt is equal to, apply the chain rule, we get pi root 2, and now differentiate L square with respect to L. So we get 2L, and into differentiation of L with respect to time, that is dl by dt. So from here when we simplify, we get root 2 pi L into dl by dt. Okay, this is your rate of change of surface area with respect to time, but in the question this is given 2 centimeter square per second. So just equate. So when L is equal to 4 centimeter, it's clearly mentioned when the slant height is 4 centimeter. So when L is equal to 4 centimeter, we get dl by dt is equal to 2 by root 2 pi into 4. We just substitute the value of ds by dt, and L is equal to 4 centimeter. So rate of change of slant height when L is equal to 4 centimeter, then the rate of change of slant height of water is dl by dt, that is equal to 2 by root 2 pi into 4, and when we simplify, we get 1 by 2 root 2 pi, that is root 2 by 4 pi centimeter per second. Clear? Okay, question number 6. A spherical balloon is being inflated at the rate of 35 centimeter per minute. The rate of increase in the surface area in centimeter square per minute of the balloon when its diameter is 14 centimeter. So there is a balloon, spherical balloon, and is being inflated at the rate of 35 centimeter per minute. That means the rate of change of volume of the balloon is 35 centimeter per minute. So if you consider volume as V of this balloon, then dV by dt is equal to 35 centimeter per minute. Clear? Now, the rate of increase in the surface area of the balloon. So, in this question we are asked for what is the rate of change of surface area, that is ds by dt, when diameter is 14 centimeter. And options are option A 10, option B root 10, option C 100, and option D 10 root 10. Okay. So correct answer is option A, that is 10. So let's solve. We know that volume of a sphere is given by 4 by 3 pi r cube. So when we differentiate this with respect to time, we get dv by dt is equal to 4 by 3 pi, differentiation of r cube is 3r square with respect to r into dr by dt. We just apply the chain rule to differentiate this with respect to time. So d by dt is equal to 4 by 3 pi 3r square dr by dt. Now it is given that rate of change of volume, that is volume is being inflated at the rate of 35 centimeter per minute, that is rate of change of volume with respect to time is 35. So we get 35 is equal to, and what is diameter? Diameter is 14 centimeter. So what is radius? Diameter by 2, that is 7. So in place of r we substitute 7. So 35 is equal to 4 pi 7 square dr by dt. So from here we get dr by dt is equal to 5 by 28 pi. So now we have to calculate rate of increase in the surface area of the balloon when diameter is 14 centimeter. So surface area of this sphere is given by 4 pi r square. So we have to find ds by dt. So just differentiate it with respect to time. So ds by dt is equal to, apply the chain rule. So differentiation of 4 pi r square is 8 pi r dr by dt. Just take 4 pi and differentiation of r square with respect to r, that is 2r, into differentiation of r with respect to time, that is dr by dt. Now substitute the value of r and dr by dt that we already calculated, that is 5 by 28 pi. So we get 8 pi into 7 into 5 by 28 pi. So when we simplify it, we get 8 centimeter square per minute. So the rate of change of surface area, rate of increase of surface area of the balloon when spherical balloon is inflated at the rate of 35 centimeter per minute, and when the specifically the diameter is 14 centimeter, is 10 centimeter square per minute. So correct answer is option A. Clear? So in today's class we covered application of derivative, its theory portion, and also we practice some question related to application of derivative. Okay. I hope the lesson was helpful. Thank you.
Hello everyone. In today's lecture, we are going to learn about thermal properties of matter and thermodynamics. This is theory part 2. Okay? This is our disclaimer. So if we talk about the trend analysis according to last 5 years of the chapter thermodynamics, so we can say overall weightage is 2.9%. Okay? And if we talk about yearly quotient distribution, so we can say in 2024 question asked from first law of thermodynamics, specific heat capacity. Okay, and number of questions 1. If we talk about their difficulty level, so we can say question was average. In 2023 question asked from thermodynamic processes, and number of questions 1, and their difficulty level average. In 2022 question asked from thermodynamic processes, again number of questions 1, and their difficulty level we can say question was average. But in 2021 again here question asked from thermodynamic processes, but the number of questions is 2, and both questions was easy. Okay, and in 2020 question asked from thermodynamic process, number of questions 1, and their difficulty level average. Okay, so these concepts are very important for the exam. All right, so let's look at the index, the topics which we are going to cover. The first is zeroth law of thermodynamics. Then we will study some thermodynamic terms. Then we will study work. Then first law of thermodynamics. After that we will look at the sign convention. Okay, then thermodynamic processes, then second law of thermodynamics, then we will study reversible and irreversible processes. Next we will discuss the cyclic process, and last we will study equation of state of a perfect gas. So these are the topics that we will cover in today's lecture. Okay everyone, so our first topic is the zeroth law of thermodynamics. So we can say the zeroth law of thermodynamics states that two systems are in thermal equilibrium. Okay, so let's assume we have two systems. One system is B and other system is C. Both system B and system C are in thermal equilibrium. Okay, both system B and system C are in thermal equilibrium with system A. Okay, it means system B are in thermal equilibrium with system A and system C are in thermal equilibrium with system A. Okay, so here we can say system C and system B both are in thermal equilibrium. It means system C and system B are both are in thermal equilibrium as shown in the figure. Then we can say that B and C will also be in thermal equilibrium, and this is the zeroth law of thermodynamics. Okay, In short, we can say if A and B are in thermal equilibrium, A and C are in thermal equilibrium, then B and C are in thermal equilibrium. And this is the zeroth law of thermodynamics. Okay, everyone. Now we will discuss some thermodynamic terms. The first comes internal energy. Okay, internal energy is the energy that molecules and atom possesses. So let's look at the definition. The internal energy of a system is the sum of the total kinetic energy of all particles in the system and the total potential energy due to interactions between all those particles. So the internal energy of an ideal gas is purely kinetic. This means in the case of an ideal gas, internal energy is purely kinetic because in the case of an ideal gas, intermolecular interactions are considered negligible, due to which the total potential energy becomes zero and only kinetic energy is considered. So the internal energy of an ideal gas is given as U equal to Fy2 into nRT. Okay, this one. Here U is the internal energy, F is the degree of freedom, okay, and N is the number of moles, R is the gas constant and T is the temperature. Okay, everyone. And the formula for the change in internal energy is delta U equal to Fy2 nR delta T. And in this case and this is the and here this is equal to NCV delta T because Cv equal to Fy2 Fy2 R. Okay, for an ideal gas, and delta T is a change in temperature. Cv means specific heat at constant volume. Now look at here in this diagram. So this is pressure volume graph. So in the case of non-ideal gases, internal energy does not depend solely on temperature but also on pressure, because in the case of non-ideal gases, intermolecular interactions exist, due to which the total potential energy of the particles is non-zero, which varies with pressure variations. Okay, so an important characteristics of internal energy is which we observe in PV representation, where pressure is on the y-axis and volume is on the x-axis. Look at here. Okay, pressure on y-axis and volume on x-axis. All right. So here we see point 1 and point 2. All right. Point 1 this one and point 2 this one. So this is point 2. All right. Here suppose molecules travels two paths, path 1 and path 2nd. Okay, between point 1 and point 2 as shown in the figure. So in path 1 the change in internal energy will be delta U, and in path 2 what will be the change in internal energy? So we can say the change in internal energy will be delta U prime. Now what will be the difference between delta U and delta U prime? Think about it. So there is a no change. both will be the same. Why? Because internal energy is a state function. Now what is the state function? This means that internal energy depends on the initial and final states, not on the path. If we also create a third part between point 1 and point 2, the path, then the path 1, path 2nd and path 3rd, the change in internal energy will be same in all three paths, first, second and third. So we can say here as a conclusion, internal energy is a path independent. It depends on initial and final point. If the initial and final point is same, in that case internal energy will be 0. Okay everyone? The next topic is work. If we want to determine the work done by the system, consider a system inside a cylinder. Okay, so we have a cylinder here. Look at here. Inside the cylinder there is a movable piston and the volume of the system can change. This system can be a gas, liquid or solid. Suppose that the cross sectional area of the cylinder is A and P is the pressure exerted by the system on the face of the piston. Look at here. It will be P pressure, or we can say P external. Okay, as shown in the figure. When the system exerts pressure on the face of the piston, in that case the work done by the system on the surroundings for a small displacement dx will be dw equal to pa dx, where a dx represents the small change in volume, which we can write as dv. Okay, so the formula for the work done is w equal to integration dw. So integration from initial volume Vi to final volume Vf, pdv. Alright, so this is the work done for a finite change in volume from initial volume Vi to final volume Vf. Okay everyone? Alright. Okay, so this is all about work. Now, suppose if the volume of the system is increasing, then the work being done by the system is considered positive. Okay, and if the volume is increasing and work is done by the system, so here we assume work will be positive. Okay, and in the second case, if the volume of the system is decreasing, okay, it is considered work done on the system, and that will be negative work. All right, so when we understand it graphically, if we look at the PV representation as shown in the figure, look at here, this one. Then if we want to find the work done, we will take the area under the PV curve. Alright, and the area that lies between the initial volume and the final volume under the PV curve, that the same area will represent work done. Okay, so here area under the shaded region, this one is P into delta V. The next topic is first law of thermodynamics. This is very important for the exam. Alright. So according to first law of thermodynamics, the heat supplied to a system delta Q is equal to the sum of the increase in internal energy. Okay, and delta U here in heat supplied to a system is delta Q and increase in internal energy is delta U, and the work done by the system on the surroundings is delta W. Alright. So mathematically we can write delta Q equal to delta U plus delta W. Alright. Here delta Q is the heat energy supplied to the system and delta U is the change in the system's internal energy, and delta W is the work done by the system. This implies that when we supply heat to a system, in that case system's internal energy will increase and the system will perform some work. Okay. Thus, the first law of thermodynamics is based on principle of conservation of energy. So we can say first law of thermodynamics based on principle of conservation of energy. Alright. So now let's understand this with the help of a diagram. So suppose there is a container, okay, and some liquid is present in that container, in this container. Alright. So if we supply heat to it, its temperature increases, and as we provide more and more heat to it, its volume also start to increase. So after supplying heat, the system's internal energy changed, and it also performed work on the surroundings. Alright, clear? Yes or no? Any doubt here? VK Versa, Karthik. All right, good. Now we will study sign convention. So sign convention is a very important. Okay, it makes it easy to numerical solve any problems. Numerically solve any problems. So delta Q here uh, is positive. Uh, Here this one delta Q. Okay, error mistake. Delta Q this one. Delta Q. This one is delta Q. So delta Q is positive when heat is supplied as represented in figure. Alright. And heat will be negative when heat is rejected. So suppose the system rejected some heat. In that case delta Q will be negative. Okay. Rejected the arrow. This arrow here shows the this one outside the system, it means rejected. And now delta U is positive when temperature increases. So when temperature increases, internal energy increases. Okay, and delta U is negative when the temperature decreases. And now let's talk about work done. So work done will be positive if the system has done work on the surroundings. All right, so in this case volume of the system will increase. All right. And if work is done on the system, then we will say work done will be negative as shown in the figure. Okay, so work done by the system occurs in the case of expansion, and on the system occurs in the case of compression. So when the system's volume decreases. All right. Now we will discuss different types of thermodynamic processes and look at the formula for work done in those processes. Okay, so a thermodynamic process is a process in which a state of system changes, and in this thermodynamic variables such as pressure, volume, temperature, etc. change. Okay, so in this process the work done either by the system on the surroundings or by the surroundings on the system is called external work. Okay, so this is that is whenever a thermodynamic change occurs in the system, the work done whether by the system on the surroundings or by the surroundings on the systems. Okay, mathematically the formula for the external work is W external is equal to integration here V1 int integration V1 to V2 PdV, which is equal to area under PV curve. All right, so area under PV curve here is the work done. As we studied earlier, if we want to find the external work, we need to see how much pressure was exerted and how much volume changed. All right, so we will integrate P dV from initial volume V1 to final volume V2. Then we will get the area under the curve, which will be the work done. Okay. Now we are studying processes. The first process is isothermal process. In this process here, or we can say uh, a process in which the temperature of the system is kept constant throughout the process, okay, or is called an isothermal process. That is, in an isothermal process the temperature will remain fixed. Now we will look at this using PV representation. So on y-axis there is a pressure, okay, and on x-axis there is volume. All right. So on y-axis there is a pressure and on x-axis there is a volume. So if we want to find work in the PV representation, we will say that the area under the curve represents how much work was done from A to B in the process. For example, work done is represented by the yellow colored area corresponding to points A to B. Okay, as shown in the figure. All right. Look at here, A to B. So volume is changed from initial volume VA to final volume VB. All right. And temperature is constant in an isothermal process. Therefore, according to Boyle's law, pressure is inversely proportional to volume. So we can also understand from the graph that there is an inverse relation between pressure and volume, and this is represented by a hyperbolic curve. That is, when the temperature is constant, pressure will be inversely proportional to volume. So according to Boyle's law, uh, we can write that PV equal to constant, and we know that molar uh, molar specific heat C is equal to delta Q divided by N into delta T. Okay, so this is the formula for calculating molar specific heat. Now we are considering the case of an isothermal process, and in the case of isothermal process we will look at the molar specific heat of the gas. So for an isothermal condition, delta T will be 0, meaning the temperature remains constant. So what will we see become? That is infinity. Okay, and the formula for the slope of PV curve at any point in the case of isothermal process will be dP upon dV equal to minus P upon V. Now let's look at the work done in the case of an isothermal process. So far we have seen that in an isothermal process the temperature is constant. Okay, temperature is constant. So the formula for work done is as follows. Delta W equals the integration from Vi to Vf, or of PdV. Here Vi is initial volume, Vf is the final volume. So we will now use the ideal gas equation PV equal to nRT and replace P with nRT by V in the formula. So nRT is constant and will come out the integration, and we will integrate 1 by V dV from Vi to Vf. Okay, and term that comes after the final calculation is nRT log Vf upon Vi. So after solving the integration you will be get the relation. So here n is the number of moles, r is the gas constant, and T is the temperature. Alright. And what is P? Tell me. What is P? Yes. What is P? Anyone? P is the pressure. Alright. Vf and Vi are the final and initial volumes of the gas respectively. So now in an isothermal process, delta T equal to 0. Hence, so in the first law of thermodynamics, delta U will be 0. So because the change in internal energy uh, directly depends on the change in temperature. So we know that first law of thermodynamics is delta Q equal to delta U plus delta W. So for an isothermal process, think about it. For an isothermal process, the first law of thermodynamics becomes delta Q equal to delta W. Okay, everyone? So in an isothermal process, the heat supplied to the system is entirely used in work done, which is done by the system against the surroundings. So that is, in an isothermal process, the heat supplied is used in work done against external surroundings. Now we are going to study adiabatic process. So an adiabatic process is a process in which the exchange of heat with the surroundings is zero. This means in the process there is a no heat exchange between the system and its surroundings. Okay, so in an adiabatic process, pressure, volume and temperature change, but delta Q is equal to 0 and entropy remains constant. Why? Because delta S is equal to delta Q divided by T. Here delta S represents the change in entropy. So since delta Q is 0, so change in entropy will also be 0, and the system's entropy will remain constant, and this is for adiabatic process. So now this is the PV graph of uh, the adiabatic process. If we look at this on y-axis, the y-axis pressure and on the x-axis is volume. So the graph represents the adiabatic process for the adiabatic process too. So PV graph is hyperbolic. So here a curves is given for two adiabatic process at two different heat engines. Alright. Now the equation for the adiabatic process is PV gamma equal to constant. Now if we mathematically change the term using the ideal gas equation, PV equal to what? nRT. Yes or no? Then we get TV gamma minus 1 equal to constant. Alright? Clear? And what about T gamma P raised to the power 1 minus gamma? Think about it. Yes. The third equation is T gamma P raised to the power 1 minus gamma equal to constant. Okay, everyone? you need to remember specifically when you are solving numerical problems. All right. Now we will examine molar specific heat for an adiabatic process. So we know that the formula for C is delta Q divided by m delta T. Delta Q divided by n into delta T. Okay. Now in an adiabatic process, no heat exchange occurs. All right. This means delta Q is 0. Thus the value of uh, molar specific heat Q C becomes 0 divided by m into delta T. All right. So the value of C will become 0. Now the slope of the PV curve for an adiabatic process at any point is dP upon dV is equal to minus gamma P upon V. So you can also derive this from PV gamma equal to constant. All right. Now the next topic is work done in an adiabatic process. So in an adiabatic process, the work done is delta W equal to integration from Vi to Vf of PdV, which is equal to mu r divided by gamma minus 1 into Ti minus Tf. Here Ti is the initial temperature, Tf is the final temperature. Now in adiabatic conditions, we know that no heat exchange occurs. So keeping this in mind, this is the final formula obtained. All right. So during adiabatic expansion, that is in the case of adiabatic expansion, delta W is positive. Therefore, the gas temperature decreases, meaning adiabatic expansion always occurs with cooling. So as per first law of thermodynamics. If we talk about the first law of thermodynamics, then delta Q change in internal energy plus work done. So in an adiabatic process, delta Q equal to 0. Therefore, the internal energy will be minus delta W. Free expansion is also an adiabatic process. All right, clear? All right. So in the case of free expansion, work done is 0, meaning no work is done on the system. Nor does the system do work on the surroundings. Therefore, according to first law of thermodynamics, delta U equal to 0 in free expansion. And this means that the final and initial values of internal energy are equal in free expansion. Next topic is isochoric process. An isochoric process is a thermodynamic process in which volume remains constant. So the volume remains constant, it does not change with time. In an isochoric process, if the mass of a gas is given, then pressure is directly proportional to temperature. All right. So in an isochoric process, volume is constant, therefore pressure is directly proportional to temperature. So we can write PV equal to nRT. This means P by T equal to constant. This can be also be seen from PV graph. So in a PV graph for an isochoric process, pressure on the y-axis and volume is on x-axis. Here volume is shown as constant while pressure is varying. So in this case there is a no volume expansion. Next is molar specific heat of a gas under isochoric condition. So the formula for molar specific heat for an isochoric process is Cv equal to F by 2 divided by 2R. F by 2 into R, okay, where F is the number of degrees of freedom. Alright. So in an isochoric process, volume always remains constant. Therefore, there is a no change in volume. The formula for work done is delta W equal to integration P dV. But because volume does not change, meaning dV is equal to 0. Therefore, work done is also 0, meaning delta W equal to 0. According to first law of thermodynamics, when work done is 0, then the heat delta Q given to or taken from the system is entirely used to change the internal energy delta U. Therefore, we write delta QV equal to delta U equal to mu CV delta T, which is equal to mu R divided by gamma minus 1 into delta T. Here mu represents uh, number of moles, of gas. Okay, Cv is the molar specific heat capacity, which increases the temperature when heat is supplied to the gas at constant volume. Okay, and R is the gas constant and gamma is the adiabatic ratio. So this means that in an isochoric process, the internal energy of gas changes when an increase or decrease in its temperature. And because work done is 0, so all the heat is converted into internal energy. Alright, clear? The next is isobaric process. So this is a process in which pressure remains constant. So if there is a no confusion, you can remember that bar is a part of isobaric and bar is a unit of pressure. So from this you can remember that isobaric means pressure remains constant. For instance, in an isobaric process, if the mass of the gas is given, then from the ideal gas equation PV equal to nRT. So volume V is directly proportional to temperature T. This means V by T will be equal to 0 or equal to constant. Now in a PV diagram, observe that volume changes, okay, but pressure remains constant. Here we see that whether the volume increases or decreases, pressure does not change. It remains constant. This means that in both cases the expansion and compression pressure remains constant. Okay. So graph A represents isobaric and graph B represents uh, iso. Graph A represents isobaric. Okay. And graph B represents isobaric compression. Okay, this is the compression case and this is the expansion case. So the work done in an isobaric process, how is it calculated? So in an isobaric process, uh, pressure remains constant, meaning pressure does not change. So the formula for W work done in the process is delta W equal to integration P dV equal to P as a constant and integration Bi to Vf dV. Alright. Why P outside? Think about it. Tell me the answer. Because the process is isobaric. Here pressure is constant. So we take is outside. Since pressure is constant, we can easily solve this integral to get delta W equal to P into Vf minus Vi, which is equal to P into delta V. Thus work done is the product of pressure and change in volume. So in this process, the molar specific heat of gas is Cp, uh, which indicates how much heat must be supplied to 1 mole of gas at constant pressure to raise its temperature by 1 unit. So its formula is Cp equal to uh, F by 2 plus 1 into R. Okay, so it is equal to Cp plus R. Here F represents degree of freedom of the gas. Alright, any doubt here? If you have any doubt, please ask. Everyone, any doubt? Yes or no? VK, Varsha, Karthik, any doubt here? If you have any doubt, please ask. Alright. Now we are going to discuss second law of thermodynamics. So two most common statements of second law of thermodynamics are given below. The first is Clausius statement. Okay, so we have a Clausius statement. So the Clausius statement uh, asserts that no process is possible. Sole result is the transfer of heat from a colder object to a hotter object. That is, no such process is possible in which heat is transferred solely from a colder object to a hotter object. So we assume that we have an object whose temperature is Th. Okay, so according to this statement, no such process is possible. Okay, where this colder object whose temperature is lower, Tc, so supplies heat to the hotter body object. If this is to be done, then the some work must be performed on the system. Only then will this be possible. So that is, work must be added to transfer heat from a colder object to the hotter object. Okay, if we push for a heat to move from a colder object to hotter object, then we must perform some external work, such as using machine or a refrigerator. Second statement is Kelvin-Planck statement. So according to Kelvin-Planck statement, no process is possible whose sole result is the absorption of heat from a reservoir and the complete conversion of heat into work. Okay, now comes reversible or irreversible process. Okay, so reversible and irreversible process are an important topic. It is essential to understand them. So a reversible process is a thermodynamic process in which the process from initial state I to final state F is reversible, meaning if the process is reversed, both the system and surroundings return to their original state without any other change anywhere in the universe. This means that the path taken from the initial state to the final state can be retraced or reversed. Therefore, we call this process a reversible process. Okay. If we look at an example, so one example of reversible process is ice melting into water, meaning ice converts into water and water can turn back into ice. So this is an one example, and another example, evaporating into water. All right, so meaning water converts into vapor and vapor can turn back into water when suitable conditions are met. So both processes, melting of ice and evaporation of water, are reversible processes, but some suitable conditions applied to them. Now comes the irreversible process. So an irreversible process is a thermodynamic process that cannot be reversed in the opposite direction. It is called an irreversible process. Okay, if you understand, suppose there are two containers with different gases, but their pressures are different. Okay, so the gas pressure in a container A is different and the gas pressure in container B is different. If we mix both gases, separating them will become impossible. So we cannot put them back into separate containers, so we cannot separate them. So this becomes an example of irreversible process. Okay everyone, any doubt here? Yes or no? If you have, please ask. All right, next is cyclic process. So a cyclic process is a process in which any particle returns to its initial state. Since the internal energy is a state variable for a cyclic process, delta U meaning the change in internal energy will be 0. So suppose a process occurs between point A and point B, okay, through a path X, and then the systems return from point B to a point A through path Y, then its initial and final position will be same. So in this case the change in internal energy will be 0, because the internal energy does not depend on the state. So in the case of entropy 2, it is a state function which depends on the initial and final position. Alright, so according to first law of thermodynamics, for a cyclic process the total heat absorbed by the system is equal to the work done. This means if we apply the first law of thermodynamics, then delta Q is equal to delta U plus work done. But for a cyclic process, delta U becomes 0. So when we put delta U equal to 0 in the first law of thermodynamics, then the heat supply, meaning delta Q, becomes equal to work done. Okay. So in PV diagrams, the volume is on x-axis and pressure is on y-axis. So when we go from point A to point B and then return from point B to point A, the initial and final state remain the same. Alright, therefore we can say that this is a cyclic process. Alright everyone. Now we will look at the equation of state of a perfect gas. So the connection that exists between state variables is called equation of state. That is, the equation of state is a relation between state variables. For example, let's talk about an ideal gas. For an ideal gas, the equation of state is PV equal to nRT. Okay, so this is PV equal nRT is the equation of state for an ideal gas. Here PV is pressure, V is volume, and number of moles are constant, and T temperature. So now if we talk about 1 mole of a gas, then the value of N will be 1. Then PV upon T is equal to R, and R is a constant term. Okay, and we can also write it as PV equal to RT, where R is a universal gas constant, and the SI unit of gas constant is joule per mole Kelvin, and its value is 8.314 joule per mole Kelvin, or if you multiply 8.314 by 10 to the power of 7, you get erg per mole Kelvin, or 2 calorie per mole Kelvin. Okay, so these are the values of R in different units. And the dimension formula is m L square T raised to the power minus 2 per Kelvin per mole. And the perfect gas equation for a single molecule PV equal to kT. Here number of mole is 1. And the next is Boltzmann constant. All right. So which is expressed in terms of universal gas constant. It is denoted by K. So this K is equal to R divided by N, where R is 8.31 and N is Avogadro's number, which is equal to 6.023 multiplied by 10 to the power 23. So when you calculate this, you will get 1.38 into 10 to the power of minus 23 joule per Kelvin. And its dimension formula are ml square T raised to the power minus 2 per Kelvin. Okay. So this is the equation of state. All right. Any doubt? Thank you for your attention. Now we are going to solve some practice questions based on these topics. So everyone, are you ready for the practice questions? Yes or no? Ready? Ready for the practice questions? VK Varsa Karthik. All right. Hello everyone. Now we are going to solve some practice questions based on thermal properties of matter and thermodynamics. This is our disclaimer. So here we will solve some practice questions based on thermodynamics and thermal properties of matter. So the first question, an ideal gas undergoes 4 different processes from the same initial state. 4 processes are adiabatic, isothermal, isobaric and isochoric. Out of first, second and third and fourth, which one is adiabatic? Okay, so in the figure, processes 1, 2 and 3, 1, 2, 3 and 4 are given. So we need to identify which of these 4 is adiabatic process. So there is a 4 options. Option A 4, option B 3, option C 2, and option D 1. So which one is correct? Please try to solve this question, everyone. Yes, please solve. Which one is correct? Yes, tell me. So the correct option is C. Okay. So we need to find out which of the 4 process is adiabatic. So here option C is correct, meaning second process is adiabatic. Let's see how. So you can see that in the question a PV graph is given, okay, and 4 processes are given. So we know that in an adiabatic process, delta Q, that is the heat exchange with surroundings, is 0. So the first process cannot be adiabatic because here the volume is constant and this represents an isochoric process. The fourth process also cannot be adiabatic, yes or no? Because in this process the pressure is constant, which represents an isobaric process. So the first and fourth processes cannot be adiabatic. Now let's see which process among the second and third is adiabatic. To calculate this, we will take the slope of this PV curve. Okay, everyone. So let's look at the slope of PV curve for an isothermal process. For an isothermal process, if we say then we know that the ideal gas is PV equal to nRT. In an isothermal process, temperature is constant. So in PV equal to nRT temperature, T is the temperature, R is the gas constant. So we can say PV equal to constant. Now we will take its derivative. When we take its derivative, then first P remains as it is. The derivative of V become dB plus V remains as it is. Okay, and the derivative of P become dP. The derivative of a constant, we know that is it is 0. So here the equation is formed, P dV plus V dB equal to 0. All right. Now so after solving the previous equation, we obtain dP upon dV equals minus P upon V. Let's first consider this equation as first. Okay. And second is the adiabatic process. For an adiabatic process, what is the slope of PV curve? Let's see. Okay, everyone. So we know that for an adiabatic process, PV raised to gamma equals to constant. So just as we took the derivative of PV equal to nRT, similarly we will take the derivative as here as well. So P remains as it is, and we will take the derivative of V to the gamma power gamma. So gamma will multiply with V, and V prime's power will become gamma minus 1. So what remains? V to the power gamma minus 1 and the derivative of V. So dV here dV plus V gamma as it is, and the derivative of P V dV equals to 0. So after taking the derivative of this equation, we get this term P gamma V gamma minus 1 dV plus V gamma dP equal to 0. So we will simplify this term. So dP upon dV will be equal to minus gamma P upon V. So we will consider this equation as equation second. Now observe as the graph is given. Okay, so curve first represents the isochoric process and curve 4 represents the isobaric process. Now two curves remains second and third. Okay, so to find out these two curves, we took the slope of the isothermal process and the adiabatic process. So out of second and third, one is the isothermal and other is adiabatic. Now the point to note here is that the slope obtained in the isothermal process dP upon dV equals minus P upon V, and the slope obtained in adiabatic process dP upon dV equals minus gamma P upon V. So when we compare both, the slope in adiabatic process is gamma times greater. Okay, yes or no? So we know that the slope of curve second is greater than the slope of curve third. So the slope is greater than the former because it is gamma times. So the curve second represents the adiabatic process. So we have identified the adiabatic curve, which is the second one, and the third curve is for isothermal process. Clear everyone? Second question, next question. Equal masses of two liquids A and B are contained in a vessels of negligible heat capacity are supplied heat at same rate. The temperature time graph for the two liquids are shown in the figure. If S represents specific heat and L represents latent heat of liquid, okay, then which option is correct? So here you have to find out the relation between S and L for both liquids A and B. Alright, please solve this question. After that, we will provide the solution of this question. Okay, everyone? Which one is correct? So option D is correct option. Okay, which states that the specific heat of liquid A is less than the specific heat of liquid B, and the latent heat for liquid A is greater than the latent heat of for liquid B. So we know that Q is heat, so the heat supplied is equal to ms delta T, where m means mass and S represents specific heat. Delta T represents change in temperature. So heat supplied to both liquids A and B was supplied at the same rate, and the mass of both liquids is also same. Therefore, we have simplified the equation here in terms of rate of heat supply. So the equation becomes P into T equal to ms into delta T, where P equal to Q by T, which is equal to rate at which heat is supplied. Alright, I think clear. Yes or no? So if we see on what specific S depends, then specific heat is inversely proportional to the slope of the temperature time graph, where delta T upon T is equal to slope of temperature time graph. So using these concepts, we find the final solution. So we can observe that the slope of the temperature time graph for liquid A is greater than the slope of for liquid B. Therefore, the specific heat of A is less than the specific heat of B. So SA is less than SB. Alright. Now comes the case of latent heat. So L represents latent heat. So when phase change occurs, a horizontal plot is formed which represents that during phase change the temperature of the sample does not change. Okay. So we determine in which liquid's case, so the latent heat is greater from the horizontal portion of these plots. Okay. So in the case where the length of the horizontal portion is greater, the latent heat is greater in that case. So in the case of liquid A, the length of the horizontal portion of the plot is greater as compared to B. So A is taking more time to vaporize, which is why the horizontal portion is larger for A. Therefore, LA latent heat of A is greater than the latent heat of B, LB. PB plots for two gases during adiabatic process are shown in the figure. Plot 1 and plot 2 should correspond respectively to what? So these are the two here we have to tell that plots first and plot second correspond to which gases respectively. Given options: option A helium and oxygen gas, option B oxygen and helium, option C helium and argon, and option D oxygen and nitrogen. Which one is the correct? Please try to solve this question, everyone. So the correct option is B here. We know that an adiabatic process is being discussed here. So for an adiabatic process, PV gamma equal to constant. Here gamma indicates atomicity and it also called the adiabatic ratio. So for monoatomic gas, gamma equal to 1.67, and for diatomic gas is 1.4. And if we compare the values for monatomic and diatomic, then which is the greater? For a monatomic gas, the value of gamma is numerically higher. Now we look at the expression for the slope of PV graph for an adiabatic process. So for an adiabatic gas, the slope is dP upon dV equal to minus gamma into P upon V. Okay, how is this known? Tell me. From PV gamma equal to constant, when you take the derivative of PV gamma equal to constant, then this expression for the slope will be obtained. Now, so according to the figure, the slope of second curve, that is the slope of curve second is the greater than the slope of curve first. Because the slope is directly proportional to gamma, therefore the value of gamma 2 is greater than gamma 1. Okay, gamma is greater than for monatomic gas as compared to diatomic gas. So the value of gamma will be higher for helium gas compared to oxygen gas. Therefore, the slope of adiabatic curve will be higher for helium gas as compared to oxygen gas. So curve 1 represents the adiabatic process for oxygen gas and curve 2 represents helium gas. Next question. Figure shows the variation in temperature delta T with the amount of heat supplied Q in an isobaric process corresponding to a monoatomic, diatomic and a polyatomic gas. The initial state of all the gases are the same and the scale for the axes coincide. Ignoring vibrational degrees of freedom, The lines A, B and C respectively correspond to what? Given options A, B, C, D. So which one is correct? Which type of gas do lines A, B, C, D respectively to? Tell me. Please solve this question. After that, we will provide the solution of this question. Please try to solve. So the correct option is C, which states that lines A, B, C indicate polyatomic, diatomic and monatomic gases respectively. So we know that for formula for gamma is gamma equals Cp divided by Cv. Here Cp means molar specific heat at constant pressure and Cv means molar specific heat at constant volume. And this term equals 1 plus 2 divided by F. Okay. So now what is the F here? Degree of freedom. Alright. So we discussed degree of freedom here because in a monatomic, diatomic, isobaric processes where pressure remains constant. Okay. So the heat added to or removed from the system is related to the change in temperature through the equation. So Q equal to NCP into delta T. So rearranging this equation to find the ratio of heat transfer to the temperature change, we get del Q upon delta T equal to NCP. N equal N is same since initial state is same for all. Okay. Now here we are discussing the molar specific heat capacity. So we know Cp equal to F by Fr divided by 2 plus R. So for a monatomic gas, F equal to 3, therefore Cp m equal to 3 by 2 into R plus R, which is equal to 5 R by 2. It means 2.5 R. Cpd equal to 5 by 2 into R plus R equal to 7 R divided by 2 equal to 3.5 R. Why? Because F equal to 5. And for polyatomic gas F equal to 6, it is assumed. So therefore Cp for polyatomic is equal to 6R divided by 2 plus R equal to 3R plus R equal to 4R. Alright. So in this way we can specify that Cp P greater than Cp D greater than Cp M, meaning the specific heat of a polyatomic gas is the highest than diatomic and the lowest is that of a monatomic gas. For this reason, the slope of their graphs are also in this order. Slope P greater than slope D and slope M. Okay. A certain amount of gas is taken of through a cyclic process ABCDA that has two isobars, one isochoric and other isothermal. So the cycle can be represented on PV indicator diagram as this one. So which one is the correct diagram? Please think about it and try to solve this question, everyone. Yes, which one is correct? So the correct option is D. So let's discuss the solution. So let's analyze this PV diagram. In this graph, we are given four processes. AB, BC, CD and DA. Among these, in some processes, the gaseous pressure remains constant. In some, the volume remains constant, and in some, the temperature remains constant. Okay. So in the processes BC and DA are the pressure is constant. All right. BC and DA. DA. This one. When the pressure is constant, the volume changes. It is called isobaric process. In process AB, the volume is constant. This means the gas is in a fixed volume and the pressure and temperature can change. So when the volume is fixed, it is called an isobaric process. Okay. So in the process CD, C2D, the temperature is constant. So this process is called an isothermal process. So in these, the temperature does not change, but pressure and volume are in an inverse relation. Therefore, uh, its PV graph shows a hyperbolic curve where when volume increases, pressure decreases, and when volume decreases and pressure increases. Okay, so therefore the diagram given in option D exactly explains the scenario given in the question. Alright everyone, any doubt? Any doubt? Karthik? Varsha? Yes or no? Any doubt here? Alright. Thank you for your attention. That's all for the today's lecture. In next lecture, we will solve more questions based on thermal properties of matter and thermodynamics. Okay everyone? Thank you for your attention. Thank you.